Nick. So, dear the Dean of Faculty of Mining and Petroleum, Professor Rido Krisnawati Mena, the Vice Dean of the Academics Affairs, Dr. Syafrizal, the Vice Dean of the
Recording in progress.
Resources Management, Dr. Susanti Alawiyah, and the distinguished keynote speakers in our conference, Professor Nick Rolison from Cambridge University, Professor Akbar Ramdhani from Swinburne University, and Professor Katsuaki Koike from Kyoto University, Professor Jian Zhao from Monash University, Professor Ki Bokmin from Seoul National University, and Professor Bei from Sejong University. On behalf of the committee of this conference, I would like to welcome all of you to the third International Conference on Geoscience and Earth Resources Engineering 2021. I would like also to extend my warm welcome to the honorable speakers from overseas. So this year, Faculty of Mining and Petroleum Engineering, FITB, hosting an annual international conference. In this annual conference, we show or we present the research jointly conducted by the researchers from FTTM, as well as with their counterpartner from international. In this occasion is planned for a gathering place or gathering moment for sharing and disseminating the achievement already obtained during the great collaboration between FTTM and their international counterparts. This conference is not limited, of course, this conference is not limited for FTTM member, but we are also inviting some people from Indonesian government institution, also from the industry, and also from our students. This conference will be divided into 2 sessions, and each session will last for about 1.5 hours, in which the first session will be hosted by Dr. Taufik Hidayat, and the second session will be moderated by Mr. Bilal Aslam. We hope this conference will bring fruitful discussion among the researchers, among the government institutions which will come to this conference. So we hope that a broader topic or more integrated topic could be proposed or could be conducted by, especially by researchers from FTTM and their international partner after this conference. Okay, maybe that's introduction from me. Without further ado, I would like to give the opportunity to Professor Rido Krisnawati Mena as our Dean to formally open this conference. Please, Pak Rido.
Okay, thank you, David. Good morning, Nick, Rolison. Good afternoon, everybody. On behalf of our faculty, Faculty of Mining and Petroleum Engineering, I would like to express my sincere thanks, particularly to all the keynote speakers for accepting our invitation to share your experiences to the attendees of this conference. During the pandemic, of course, we have a very limited chances to have a direct meeting, direct discussion, but I believe by using this type of online discussion, online conference, we can still share our knowledge, we can still share our experience, our findings in our research to the participant. Because I believe the participants are mostly students, and also, as David said, some of practitioners from the industry and from the government. Thank you for accepting our invitation. Thank you for preparing your talk for today conference with very short notice. For example, I got answer from Professor Kibokmin only, and also from Professor Jiang Sao only one day. So thank you very much, Kibok and Jiang, for accepting directly our invitation. So I would like us to start the conference. So on behalf of the Faculty of Mining and Petroleum Engineering, I declare that the conference is officially open. Thank you very much.
About for in the next 3 years, 3 hours. I'm sorry, next 3 hours. So for the first session, we will have Dr. Taufik Hidayat. Will be the chair of the first session. Dr. Taufik is an assistant professor in metallurgical engineering of ITB, and he earned his PhD from University of Queensland in 2013. And since then, he has performed so many excellent research and published several high-quality journals. So please, Dr. Taufik, to open the first session.
Okay, thank you very much, Dr. David Sahara. Good afternoon for everyone joining from Indonesia, Korea, and Japan. And good morning for everyone joining from UK, and good evening for everyone joining from Australia. As Dr. David Sahara has mentioned, my name is Taufik Hidayat. I'm one of the lecturers at the Metallurgical Engineering Department, Institut Teknologi Bandung, and I will act as the moderator for the first session. So again, it is our great pleasure to welcome you all to the third International Conference on Geoscience and Earth Resources. So this year theme, which has been mentioned before, is about geoscience and earth resource engineering for sustainable future. So we are fortunate to have several prominent keynote speakers from different regions covering all areas in the field of geoscience and earth resource engineering. And in this first session, we will have 3 presentations delivered by Prof. Nick Rolison, Professor Akbar Ramdhani, and Prof. Katsuaki Koike. Now I would like to introduce you our first keynote speaker. Let me open the PowerPoint to introduce Professor Nick Rolison. So Prof. Nick Rolison obtained his PhD from Monash University in 2001. He was a senior research fellow in Australian National University in 2013, and then he had a professorship at University of Aberdeen between 2013 until 2017. And now his current position is a BHP Foundation Mackenzie Professor of Earth Science since 2017 at the University of Cambridge. So Professor Nick Rolison has a large number of publications in the field of earth science, particularly seismology. And from him, this interesting talk today. Professor Nick Rolison, we have 30-minute session for you to present your material. And if you can, please in the end of your presentation for question or discussion session with the participant. And please allow me later to remind you if we only have 5 minutes left for your session. And for the participant, if you have question, you can type your question in the Q&A chat box. You will see it at the bottom of your screen. If we still have time, Professor Nick Rolison will answer the question after his presentation, but maybe if we run out of time, maybe we would like to kindly ask Professor Nick Rolison to answer the question by text in the chat box. Okay, Professor Nick Rolison, the floor is yours. You have 30 minutes from now. Thank you very much.
Okay, thank you, Taufik. I'll just share my screen. I see my. Okay, can you see that okay?
Yeah.
Yes, you can see it clearly.
Okay, great. So my talk today will be on the seismic structure of Sulawesi and Borneo, and it reflects the last 3 to 4 years of collaboration I've done with my colleagues in both Indonesia and Malaysia. And some of you may recognize this shot, which was taken from the top of Mount Kinabalu on the northern tip of Borneo. So here's an overview of my talk. I'm just going to start off by giving you a regional view of the seismic structure of Southeast Asia. So my basic aim is to start from a large scale and then gradually focus in on smaller scale work that we've been doing. So on a large scale, I'm going to talk about some body wave tomography work that I've been doing with my students, and also some adjoint waveform tomography, otherwise known as full waveform inversion. I'll then focus on results from northern Borneo, where I've done work with my Malaysian colleagues, and I will focus there on receiver functions, two-plane wave tomography and teleseismic tomography, which we've used to illuminate the structure beneath that region. I'll then move down to northern Sulawesi and investigate the subduction zone there with some work we've done recently from the point of view of receiver functions. So I'm sure many of you have seen maps like this before. So Southeast Asia is a very exciting region tectonically. And the reason for that is that we have the Australian plate moving north-northeast very rapidly at about 7 centimeters a year. And then we have the Pacific plate moving westwards, and that's resulting in this convergent zone where we have Sunderland, which is the southern end of the Eurasian plate. And we have extensive subduction zones like the Sunda Arc, wrapping itself around the bottom of the Indonesian archipelago. And similarly, we have subduction zones here and very complicated microplates in the southeast here. So the first study I'm going to talk about is body wave tomography. And this is where we exploit the arrival times of many regional earthquakes recorded by seismic networks in the region. And this data is obtained from the ISC catalogue. And this plot here on the left shows you all the earthquakes that we are using. And so you can see they range in depth from crustal down to nearly 700 kilometers deep. And so overall, it's quite a good coverage, and we can exploit that in order to image the structure using tomography. And this is the receiver coverage that we use. So you can see there's excellent coverage of the land regions, obviously not so good coverage beneath the seas and oceans. And the resulting path coverage is quite good. So in order to do the tomography, I'll be using this method called FM Tomo, which is something I devised a number of years ago for doing three-dimensional seismic tomography, where we essentially invert the arrival times for three-dimensional velocity structure. And this is the path coverage that we have available using all those receivers and sources. And so this is a projection in the horizontal plane, and you can see that the coverage is generally very good. But there are regions such as southwest of the Indonesian archipelago where the coverage isn't so great, and obviously that will be reflected in the quality of our results. And so we'll be inverting this data for both VP and VS velocity, and also the ratio between VP and VS. So I'm not going to go into any great detail about how this is done in terms of dealing with the data set, other than we spend a lot of time grooming it to remove outliers and things like that. And we use various relocation methods and so forth. And as a result, we do come up with multiple models of the seismic structure, which we can kind of interrogate together to get a better understanding of what's going on. And so here's a result that I want to focus on for a few minutes. simply because there's quite a lot of detail here and it's quite interesting. And so this is what's referred to as a vote map. And what a vote map is in seismic imaging is where we do seismic tomography and we come up with several different models using different initial conditions and different realizations of the data set. And what we do is we stack those models together according to, in this case, simply whether there's a high velocity or a low velocity. So it's binary in that sense. So where all the models agree that there's a high velocity zone, it'll be ranked, if you look at the right column here, as number 6 on this scale. Whereas if none of them have a high velocity zone in a particular spot, then it'll be ranked at 0. And so this 200-kilometer depth region, you can see that in this case, all of the 6 models that were generated, they all agree on this high velocity zone coming around here, which is unsurprising because we know we have that marks the Sunda arc, and we have a slab subducting. So at 200 kilometers depth, we would expect to see a high velocity slab, and you can see it realized very nicely coming around here. And there's a band arc where we see this slab wrapping around. And we also see a lot of detail up here in Sulawesi, where we have the Celebes Sea subducting to the south, and then the divergent double subduction here of the Maluku Sea here, and then up through the Philippine Trench. And if we take some cross sections through this, so this cross section running along here, it's a bit hard to see number 5, but that corresponds to this section here. We can see this slab here subducting down quite clearly. And then we can see the divergent double subduction over on this side, where we have a slab coming down this way and a slab coming down that way. And then this slice coming through here, again, we see the Indo-Australian plate subducting down there. And then coming through the Banda arc, you can see the Banda slab coming down very clearly and then stopping in the transition zone. And then these slices on the right here, coming down through here, focus on these slices here, 1, 2, 3, 4, as we come down here. And the main thing I want to look at is this subducting slab, the Indo-Australian plate, and you can see it in all of these slices. And in particular, what I want to look at here is this major hole in the slab there, where we also have an absence of seismicity, and it's picked out by most of the models. So it gives you a very rich tapestry of the seismic structure of Southeast Asia doing tomography in this way. And there's a lot that we can learn from models such as this. So another image I want to show you is of perturbations in the Vps ratio. And you can see the Australian plate here, and it's imaged at this depth anyway as lower Vps ratio. And that's what we would expect from continental lithosphere that's quite old. And one thing of interest here is that we have this salient coming through here in the Timor region. And that's what, again, something we would expect from other studies, which show that there is probably underthrust forearc lithosphere in this region. And then in the Banda arc region there, we can see that there is very elevated VPVS. And we put that down to the presence of partial melting, volatiles, and fluid migration in this region, where we have very complicated slab geometry, a lot of fracturing, and probably a lot of fluid ascent through the lithosphere and crust. So that's the result from body wave tomography, very briefly. And now I'm going to move on to adjoint waveform tomography. So this is full waveform inversion. And so here it's a very different ball game to body wave tomography using travel times, because here we're trying to match waveforms, and the computational cost is orders of magnitude greater. And as a result, and the reason for that is that we need to solve the full elastic wave equation in 3 dimensions. And therefore, one simulation takes a very long time. So as a result, we use much fewer sources, so only about 130 in this case. And then the colored triangles are stations to which we have data recorded. And in terms of the way the method works is we start from long periods and try and match the long period waveforms. And then we gradually add shorter and shorter periods. So we allow the waveforms to increasingly have shorter and shorter period information. Then we repeat the inversion process. So it's kind of a multi-scale tomography. And you can see here that this 100 seconds refers to the period range 100 to 150 seconds. And then we do this iterative nonlinear inversion. And once we converge to our satisfaction, we then go from 80 seconds to 150 seconds. And then we gradually go to these shorter minimum periods until we're satisfied with the result. And the reason for doing that is to overcome the nonlinearity of the inverse problem where cycle skipping can be an issue. And this plot here gives you an example of how this works. So this is a 100 to 150 second period band. So the black line is the observed waveform. The dashed line is the synthetic for our starting model, which is just a 1D reference model. And then the red line, the solid red line, is the result after 8 iterations. And you can see it fits the waveform a lot better, particularly in terms of phase, than the starting model. And then we move on to 50 seconds here. And you can see that, again, there's an improvement. And subsequently, as we go down and down, you can see the shorter and shorter period information is being added. And you can also see the emergence of body wave information more clearly, which is separate from the surface wave information. And here, this plot here shows you the evolution of the inversion. So here's our initial model. It's just one-dimensional. And then once we get to 65-second period, you can see we have the broad scale structure recovered quite well. So this is, if you look at the bottom right, this is a slice through here. So it's essentially an east-west slice. And you can see that as we gradually get to shorter and shorter period, we get more and more detail being added. And in the final case here, where we have 20-second data as our minimum period, you can see subduction zones turning up quite clearly, and we've plotted the seismicity over the top. So you can see that clearly as well. And I just wanted to show 2 representative slices. So I'll just go back to here. So the slices I'm showing you are this slice here with the brown and this one here with the black and grey. And so this one comes down through the northern Sulawesi subduction zone, and you can see the slab descending down to the transition zone very clearly. And the thing to note here is that it's very steep. And then this is the Indo-Australian plate subduction from the south coming up to the north. And then over here, if I go back to this slice again, we're going through the Banda arc. We can see subduction coming this way. We can also see subduction up here. So, and this is imaging S-wave velocity as opposed to P-wave velocity that I showed you before. And one of the notable things about full waveform inversion is it gives you much better constraint of the amplitudes of the anomalies compared to the body wave tomography. So now I'm going to move on and discuss some of the work that is more detailed in Borneo and Sulawesi. And all of these dots represent stations where I have gone out with my collaborators and deployed them in the field. So it's a very dense array in northern Borneo that was run between 2018 and 2020. And then coming down through here, through Sarawak and Kalimantan, we've deployed a number of stations through there. This very dense array is one we just deployed recently around the site of the new capital in eastern Kalimantan. And that's where we'll be doing some very detailed studying of earthquakes around that region to see what the background seismicity is like. And then these orange dots are ocean bottom seismometers that were deployed, and we have the data back now and are looking at it in the Makassar Strait and in the Celebes Sea. And then these pink stations are stations we deployed in Sulawesi a year or two ago in order to record seismicity associated with the Palu Koro Fault and the North Sulawesi subduction zone. So to start with, I'm going to have a look at the northern end of Borneo, where we have a number of results. And this is a very interesting region because it is an area of post-subduction tectonics. And this gives you a kind of schematic illustration of what the geology is thought to be like. So what we have coming down here is we have the Northwest Borneo Trench, where there was previously subduction of the Proto-South China Sea, and that ended up with continental collision, or continent-continent collision. And subsequent to that, we had the Celebes Sea subducting along this front here, which ended only about 8 or 9 million years ago. And so the result of both of those processes has affected the landscape very significantly along here. It includes features such as circular basins and this very anomalously high Mount Kinabalu. So we deployed these stations for a couple of years in order to see what's going on in the crust and upper mantle underneath. And this is one of our deployments in a palm plantation where we have our seismometer buried in the ground here, the electronics in this box, and a solar panel and GPS. So that was a typical deployment with a fence around to keep animals out. So here's an example of a receiver function transect. So this is essentially using distant earthquakes to look at the interface structure beneath the station. And so two of the things you see fairly clearly are this, as we go down this line here, we can see this reflector or rather conversion coming down through here and also down through here. So we translate this to a velocity model through inversion. In this case, we're inverting surface waves and receiver functions. What you can see here is this blue is high velocity and this sort of brown color is low velocity. And you can see there's the Mount Kinabalu here, and we're coming down this transect. And what we think we see here is some evidence of underthrusting, which is related to the dangerous grounds block, which is an extended continental block which collided with northern Borneo about 20 million years ago. So if we look at the thickness of the crust or the MOHO depth, so the depth of the base of the crust, this is what this map shows here, and it's quite interesting because it shows you quite thick crust over in the west here where we have the Crocker Range, which is the mountain range resulted from the continent-continent collision, with a peak thickness of just over 50 kilometers. And interestingly, somewhat displaced from Mount Kinabalu, which is over here, which is actually has the highest topography of about 4 kilometers, whereas over here it's much lower than that, probably 50% lower. So that's quite an interesting result. And also we have this thinner crust running through the center of northern Borneo here, and we think that's related to the opening of the Sulawesi some 9 to 15 million years ago. So the other result we have is from two-plane wave tomography, and this is using distant earthquakes and the surface waves from those distant earthquakes when they impinge upon low velocity anomalies. Then you have this effect, swallowtail effect, and the idea is to try and exploit this multiple waves that arise from heterogeneity in the Earth. So I won't go into detail how that works, but essentially at periods about above 20 or 30 seconds, we can exploit that data and come up with three-dimensional models of the shear wave velocity. And this is showing you at 20 kilometers depth, but it's consistent with our result from receiver functions in that it's suggesting that we have this low velocity zone in the deep crust, which is probably related to a very thick sediment burden that comes down through here. Over here, we have an estimate of depth to the MOHO, so it's using a proxy. And again, we see thinner crust coming through the center here, contrasting with the thicker crust beneath the Crocker Range. Then if we go down to 40 kilometers depth, this pattern is almost reversed. And the reason we see that is because at that depth, we are, where there's thinner crust, we're now in the mantle lithosphere, which has high velocities, whereas the root of the crust is still evident in these thicker crustal regions, so they end up with lower velocity. And then of particular interest over here to the right is the depth to the bottom of the lithosphere, so the base of the mantle lithosphere. So you can see it averages over 100 kilometers depth. And this is in contrast to global models, which suggest that the whole of Southeast Asia has a very thin crust. So on this scale, it's suggesting the crust here is, or the lithosphere is only about 40 kilometers thick, suggesting it basically has no mantle lithosphere, but our results show otherwise. Now, the reason for this disparity may be that these models don't have the resolution to show up this thicker lithosphere in this region. So another result I wanted to show is from teleseismic tomography. So this is where we use distant earthquakes, as shown here. And the energy comes in underneath the array. And so this shows you an example of what P-wave energy, the propagation path looks like in the Earth. And this is PK to IKP, which is a reflection off the inner core boundary. And we can exploit these arrival times in order to image the structure beneath. And this is what I'm showing you here. So the basic principle is that we have an earthquake from a long way away when the energy impinges on the lithosphere. the wavefront is fairly planar, and we can essentially look at the pattern of arrival time residuals across the array and remove this effect of the wavefront not being horizontal. And you can see this pattern, and this pattern can be related to where the lithosphere overall is fast and where it is slow. And so what we do here is we align our waveforms from an earthquake along all of the stations, and then the remaining residual is due to lateral variations in lithosphere. That's what we assume. And then we can just use cross-correlation type methods to align the waveforms. And then that residual, in other words, the difference between what we have here and what we have here in terms of differential times, we plot as a function of the station location for a particular event. You can see that there's a very clear pattern where we have energy coming in earlier in this region here and energy coming in later over here. And we can exploit that through tomography using multiple sources in order to image the three-dimensional structure. And so what I'm showing you here is a 150 kilometer slice through the P-wave velocity model. And this red line here is the slice I'm showing you here. What we see here is this higher velocity here, which we're interpreting as remnants of proto-South China Sea subduction. And then on this side here, we're interpreting this as a lithospheric drip or Rayleigh-Taylor instability. And it's been shown that, so in other words, we have a remnant slab probably over here, which we can't image because it's off the edge of the coast. But it's been shown that in this sort of circumstances, you can get instabilities in lithosphere and lithospheric drips. And so that's what we think we see over here. So now I'm just going to quickly move over to Sulawesi, where myself and my postdoc and some of our collaborators undertook a study looking at the North Sulawesi subduction zone. And you can see we have subduction coming this way. This is related seismicity, but we also have subduction coming over here from the west, and that results in these increasingly deeper earthquakes going this way, underlying the North Sulawesi subduction zone. So it's actually a very complicated tectonic region, and this slice coming through here shows you clearly the geometry of the dipping slab. And so what we've done here is we've reanalyzed some of the focal mechanisms from earthquakes in the region, and these are slices coming through here, and this one DC is through here. And what we're seeing is that this red line here is from the slab 2 global reference model for slab geometry. What we're finding is that the earthquakes that we look at actually sit above that, so that model is probably not accurate in this region. The other thing we see is from our focal mechanisms, as you go from west to east along the geometry of the trench, we see that the slip vector predicted by the focal mechanism changes orientation. So it goes basically northwest when you're on this side and then northeast when you're on this side. And you can see that coming up through here. That's also reflected in the GPS vectors here, which is shown here relative to a fixed Sunderland reference frame. And you can see basically here, they're sort of northwest. Once you come over here, they're northeast. So we looked at various models that could explain this. And if we have a simple case here of straight subduction like this and the overlying plate like that, then we'd expect focal mechanisms like that. And but in our case, we see focal mechanisms like that, but we also see normal faults oriented perpendicular to that. And so of all these possibilities, the one that we favor here is this one, because it gives rise to a pattern of focal mechanisms we actually observe. We have the subducting slab here, and then the overriding slab is actually gravitationally collapsing or flowing outwards, and that gives rise to the normal fault earthquakes. So that's what we think is happening over there. And now I'm just going to finish off with a plot showing you some receiver function results from some of the stations that we've deployed so far. And it's ongoing work, but the main thing of interest is that northern Borneo, where we have this post-subduction setting, on average seems to have thicker crust based on receiver function results compared to Sarawak and Kalimantan, although we haven't looked at this region in detail yet. And then the results for Sulawesi are somewhat scattered, and we have a lot more analysing to do. One of the challenges is that stations near the coast are quite noisy, but we hope to populate this map more and try and get a better understanding of the relationship between Borneo and Sarawak. So I'm going to conclude the talk now by just giving a few summary points. So the regional structure of Southeast Asia is quite well defined, which I hope I showed from the body wave tomography and full waveform inversion. The post-subduction setting of northern Borneo sets it apart from the rest of the island, particularly in terms of crustal thickness and mantle structure. Sulawesi exhibits very complex tectonic behavior. We have subduction of the Celebes Sea coming down from the north to the south, and then we have it transforming in the west of the Palu Koro Fault. And then underlying all of that is this deep subduction of the Halmahera slab. And as I mentioned, we hope to use our data in the next few years to establish a better tectonic connection between Sulawesi and Borneo, and also to get a better understanding of the seismic hazard in the region, which in particular that dense array I showed you deployed in East Kalimantan is aimed at doing. So I'll leave it there. Thanks for listening.
Okay, thank you very much, Professor Nick Rolison, for the excellent presentation. We have one question from the audience. Let me read it for you. Dear Professor Nick, thank you for the great presentation. I'm interested at the Sulawesi Palu Koro Fault region. I would like to ask about the tomography imaging result at this area. Could we estimate the depth of Palu Koro Fault by the tomography imaging? Okay, maybe you can answer that question, Professor Nick.
Sure, yeah, that's a very good question. Well, so far the tomography imaging we have undertaken has been on a regional scale, and at that scale we're looking at lateral variations in velocity of the order of 100 or more kilometers, and the vertical resolution is not much better than that. So at the moment, those models, we can't really say much about the Palu Koro Fault. However, with the new stations we've deployed in that region, we're currently undertaking what's known as local earthquake tomography, and that should give us a resolution to help answer that question. I mean, in terms of the depth, that could be determined from the seismicity as well. And again, one of the things we're doing is doing accurate relocation of the seismicity using the arrays we have deployed. And that, coupled with the tomography, should give us a much better understanding of the depth extent and sort of lateral, the kind of width of the fault at depth.
Okay, thank you very much. I think we still have time for one more question. There's a question from Pak Andri Hendriana, related with your work with FWI. Since you use low frequency waveforms, periods higher than 20s, then I believe that what is inverted is dominantly surface wave. Is that correct? The
Yes.
resulting velocity model may also accurate for only S wave. Thank you for your comment.
Yes, that's a very good question. As you may have seen from the waveforms I showed you, that they are dominated by surface waves, and therefore our sensitivity to seismic structure at depth is dominated by S waves. And in particular, SV is the S wave velocity type that we are most sensitive to, and our sensitivity to P wave is much poorer, which is why typically in full waveform inversion people don't typically show you a P wave velocity result, because it's not as good, and therefore that's why the focus is on S waves, and in particular the surface wave propagation. As you know, the sensitivity drops off rapidly with depth. So when you do purely surface wave tomography using standard methods, your resolution drops off in depth. But in our case, that doesn't happen as badly, because we also include the body wave component. And what we do is we use separate windows, which I didn't go into any detail of this, separate windows for the surface waves and the body waves, to try and make sure that we actually do include the body wave forms in the tomography. And so it doesn't end up being quite so surface wave dominant as it could otherwise be. So we do have sensitivity down to the transition zone, as you would have seen with the subducting slabs that I showed. So it does work better than standard surface wave tomography methods for that reason.
Okay, thank you very much for your answer. I think we have reached the end of this session, this presentation. We still have one question in the chat box. Maybe if you could kindly answer by typing into the chat box. And thank you very much. I think it's very early there at UK, maybe 7:40. We really appreciate your time. Okay, thank you very much, Professor Nick Rolison. Yeah. Okay, now let's proceed to our second keynote speaker. Our next speaker is Professor Akbar Ramdhani. Professor Akbar Ramdhani, let me show you Professor Akbar Ramdhani profile. Okay, I hope you can see the slide. So Professor Akbar Ramdhani obtained his PhD from McMaster University in 2003. He is a visiting professor at the University of Leuven in Belgium and also CSIRO. And he is also an adjunct professor at the Faculty of Engineering at University of Indonesia. And now his position is a professor in the Fluid and Process Dynamic Group, Department of Mechanical and Product Design Engineering at Swinburne University of Technology, Australia. And he has plenty of publication in the area of high temperature metal processing and material processing. Okay, Professor Akbar Ramdhani, the floor is yours. You have 30 minutes for your presentation, including a question and answer session. And for the participant, please write down your question in the Q&A box. And also later, please allow me to remind you if we only have 5 minutes left for your presentation. Okay, Professor Ramdhani, the time is yours. Thank you.
Thank you very much, Taufik. It's a pleasure for me to be here today and also meeting with you again. So it's been a while. So yeah, the topic that I'm going to talk about today is about decarbonization of metallurgical processes. So this area is currently, of course, there has been a lot of push in these nations in reducing the CO2 emission related to basically to overall to reduce the CO2 emissions to the environment. So, so I'm going to talk about something that is quite a general first, then I'm going to sort of choose one area of metallurgical processes that going to be sort of we're going to look at together, and then we'll look at also other industries and also some of the work that we've been doing at Swinburne as well. So yeah, so when we talk about the decarbonization, well, we sort of can sort of guess from the word itself. So in a way, any activities or effort to remove or reduce the CO2 output to the atmosphere from processes, from in this context, metallurgical processes, that's basically it's decarbonization. So the word decarbonization itself is also, and also the approach in decarbonization is also pretty wide as well. It ranging from, well, we basically reduce or eliminate direct emission of CO2 from any processes, right? So that or eliminate carbon emissions through the use of renewable power, avoiding the production of carbon from generating power using fossil fuel, for example, or if during the transition period where we are still producing carbon, we actually capture the carbon itself, and we store them or we reuse them for other sort of applications. And there are a number of related area when we talk about decarbonization. For example, hydrogen economy. That is the importance of hydrogen to replace carbon as a fuel and as a reductant, especially for metallurgical processes. So the context of the discussion, sometimes we also involving the use of hydrogen, for example. The second one also that commonly involved in decarbonization is the electrification, but of course energy sources rather than using fossil fuel sources, for example. For example, electrification using hydrogen itself, using solar energy, wind energy, and other sort of renewable energy sources. So when we talk about decarbonization of metallurgical processes, we can sort of target the big elephant, big targets. Yeah, so mainly the heavy industries, right? So it could be iron and steel industry, cement industry, aluminum industry, and other sort of chemical industry. So the area or the focus that I'm going to talk about today is going to be in the iron and steel making industry, because iron and steel making industry is one of the top 3 contributors to CO2 emissions. So it actually contributes to around 7% of global CO2. Yeah, so it's quite big. So if we can tackle this, of course, we can have quite an immediate impact in our decarbonization effort. Yeah. When we're talking about iron making and steel making, of this is linked to the use of coal or coke as a fuel and reductant. Right? So it's approximately about 1.8 tons of CO2 per 1 ton of steel. Yeah. So it's pretty big. And I'm going to look at the figure on the right here, which illustrate in general the process for iron and steel making. Yeah, and also we can sort of try to identify where is the CO2 emission mainly coming from, majority of them. Yeah. So when we make steel, we're first making iron, and then steel, and then we manufacture them. When we're talking about iron making, there are a route in terms of their production. One is called the integrated steel making, where we are using blast furnace to make iron, and followed by either blast oxygen BOF, blast oxygen furnace, or using electric arc furnace. Right? So if you look at this process here, the iron making one, they use a blast furnace. We are using iron ore, and then we undergo a sintering process, and that it requires energy, right? It requires heat, and for reductant and for also fuel, we also use metallurgical coal to make an oven. To make coke in coke ovens, and the coke itself is used with the sintered iron ore in blast furnace. So as you can see from here, this of course one of the major big a lot of coal for making coke in the blast furnace process. Electric steel making, or EF, where usually we started with either making the iron first, and we input that into the electric arc furnace. Now, the electric arc furnace process originally is add more and more to optimize the process. So these are the two, and then we can also composition, or the contribution, the share of this major route around the world, which means that the overall energy balance of the reactor will change, and how that actually behave, in the reactor itself, and also microscopically. Right. I just want to give you some ideas here about. Okay, we mentioned about the use of EF and also let's say 100% scrap. That's actually a good one, because if you use 100% scrap in the EF, the CO2 emission is about 400 kilograms CO2 or 0.4 ton, 400 kilograms CO2. But if that's a 100% scrap, as you increase the DRI, right, then the slight increase of, there's an increase in the emission. For example, here, if you put 80% of DRI, you get about 1,000 kilograms CO2 per ton of steel. But even with that one, for example, there's still a bit of, it's actually lower than the emissions of root of BF, blast furnace, and BOF. Yeah. So can be considered when we're talking about adding more DRI into the EAF, right? So just to get some understanding, originally the EAF, the source of energy, or EAF, is 100% from electricity, right? But recent sort of operation, more and more chemical energy is actually inputted into the reactor. For example, here the table here showing the percentage composition or the percentage contribution of coming from electrical energy, roughly about 50%, for example. Now carbon oxidation. So that's why, for example, we add carbon, we inject carbon in EF in current process, because that's also used for chemical energy to top up the electrical energy, right? And there's also other sort of oxidation reaction there. And another thing, the addition of carbon into the EF is important for forming process, which also good to do a heat to conserve heat in the process there. So so it's not as easy as, okay, we just want to run EAF without any carbon in it. There are a lot of things that needs to be considered. For example, here, if we add a DRI, and every 1% carbon in DRI can affect the process. For example, here, it can reduce the yield by about 1%, but it can increase the productivity, EF productivity, by 1% or 0.8 to 1.5. In terms of energy, if we add 1% carbon, there is a reduction of
Recording in progress.
And the quality of DRI has to be quite good, which means we need to have high quality iron ore, the original high quality iron ore with a high quality, right? So because that will affect the process as it goes throughout the process chains there. Okay, and then we talk about adding hydrogen, but there's also complication from our complexity from this aspect. We still have some problem with the economic of the green hydrogen, right? And green electricity currently still not sort of economical, for example. There's also problem with scale, right? So we need to have large amount of hydrogen if we want to replace everything with hydrogen, reverse coke hydrogen. To match, the industry, industry scale, for example. Of course, there's an issue about the manufacturing, storage, transportation, related to the use of blue and green hydrogen, for example. There's also operational perspective on sort of detailed, mechanisms of reactions, that kind of thing. operational issues, which also need to be considered, think about, how we do a foaming if we don't have carbon, for example, how we deal with residuals, gang materials, and so on. So that's in non-ferrous. That's in ferrous industries. In non-ferrous industries, just to
Professor Ramdhani, we have 5 minutes left, including question and answer.
Okay.
Yeah. Thank you.
So I'll just probably 2 more slides, 3 more slides, and then 2 more slides. Okay. So quickly, the non-ferrous industry, there's not many also, current industrial process. For example, if you're talking about the use of hydrogen, right? And for example, the production of tungsten, molybdenum, nickel, and cobalt. So these are just the metals. These are just the selected metals that currently, some of the production of these metals actually use hydrogen. Right? So particularly I want to point out in here, well, the amount is actually pretty small compared to the iron and steel industry. But one of the things that I want to point out in here is the nickel. Yeah? So production of nickel is usually using pyrometallurgy, but also there's a route using hydrometallurgy, then followed by production of nickel oxide and reduction of nickel oxide to nickel, for example. And that part, in industry, we use hydrogen to do that. So just a while back, for example, here, this is actually a work of our a moderator, Dr. Hidayat. So it's been a while, this work. So this is actually looking at the details of nickel oxide reduction by hydrogen. So when we look at details, it's not as easy as just just reduction, because the condition can affect how the nickel produce, whether it's going to be like a porous nickel, it's going to be quite dense nickel, and that will have an effect on the kinetics of the process. So this kind of detailed mechanistic sort of process will affect the overall incorporation of hydrogen into the process. Yeah. So now, because of running out of time, I will go to the summary. Basically, there are a number of approaches that can be implemented in iron and steel making industry for decarbonization, starting from the simple approach during transition period or transition stage to fully decarbonization of the process itself, for example, using 100% hydrogen or 100% sort of electricity, a combination of both. There are a number of challenges. It's not just technical, but there are also non-technical challenges in incorporating hydrogen, for example, for full decarbonization of iron and steel industry. Right? And the thing that I haven't been able to present it is we did some work in Swinburne to try to develop a new process. But what I want to mention in here that there's a need for developing a new technologies and new approaches for decarbonization of metallurgical processes. And lastly, it is actually now an exciting time for the field of metallurgy because of one of this is of course the decarbonization effort around the world, and also resource efficiency, and also recycling. So I think that conclude my talk, and I'm sorry for a bit of overtime there. I will return it to Dr. Taufik Hidayat. Thank you.
Thank you very much, Professor Akbar Ramdhani, for the great presentation in one of important topic in metallurgy, which is reducing the carbon from the processes. Yep. And we have one question from the participant from Dr. Zelatan Lega. Let me read it for you. Dear Professor Ramdhani, thank you for your presentation. It appears that changes in the technology is difficult both technically and economically. It seemed to me that attaching a carbon capture technology to steel production process may be more practical approach to quickly reduce carbon emission for this industry. My question is, there has been any commercial use on the carbon capture technology for the metallurgical industry? Okay, maybe you can answer that question, Professor Ramdhani.
Yes, so that is actually one of the way that the industry is currently doing or try to do in the transition period, because I believe in the coming years that also won't be enough, and so it is still quite expensive as well to do that. But in Australia, for example, and also around the world, that is also an effort that currently being pushed as well at the moment as a transition stage. So that technology exists, but still quite expensive. Yeah.
Okay, thank you very much, Professor Akbar Ramdhani. I think we have reached the end of this presentation. Thank you very much for your time. I know it's very late in Melbourne, and thank you for your presentation. Now, I would like to proceed to the next session from our third speaker for today. The third speaker for today is Professor Katsuaki Koike. Let me show you his profile. So Professor Katsuaki Koike is currently a professor in Department of Urban Management, Kyoto University in Japan. We can see from here, Professor Koike has a large number of publications in the field of geomodeling and mathematic geology with plenty of citation. We can see there's a huge number of citation for each of his publication. So without further ado, I would like to give the time to Professor Koike to give presentation. We have 30 minutes for you. And for the participant, again, if you have a question, you can type in the Q&A box. And later I will remind you if we only have 5 minutes left for your session. Okay, the time is yours, Professor Koike. Thank you very much.
Thank you very much for a nice introduction of me. Today I would like to talk about SATREPS and Access Bangus project for large enhancement of geothermal power generations. This is a collaboration to research the result between Kyoto University and Itebe ITB for more than 7 years. So the content composed of research background and aims, concept of that we want to find out the steam spot. So at first, I'd like to introduce what is steam spot. This is our new the technical term. The research items, content, and the study area. And for the 7 years worked, we have got many results. So I just would like to present some of a typical result. And most important is potential mapping of steam spot, the existence by data integrations. And during the survey, now we are moving to the verification stage. So the first stage is just to make a map, potential map. The next stage is verifications, how the accuracies of our predictions or estimations. So now we are going to move to next stage from the steam spot to the critical spot. So we are finding out the deeper structures in the reservoir. The research background, of course, everybody knows that we should is our duties, responsibilities over the world. So one of the typical the linear resource is geothermal. That's why that the many countries, volcanic countries, focus on enhancement, the large increase of geothermal power generations, including Indonesia and Japan. But one of the most serious issues that hinders this enhancement is the cost of exploration drillings. So because a large number of exploration wells need to be drilled at greater depths, but the success ratios to reach actual reservoir is small. That's why our motivation is how we can reduce drilling cost and increasing the success rate. So it is very difficult to use just one method. We need integrations of several geoscientific methods to find out such a good places of geothermal power generations. But we define the steam spot. The steam spot is the portions probably composed of permeable fractures with not much amount of thermal waters and steam that enables large and long-term power generations. So the overall goal is exploration drilling cost is reduced by our technologies. So, but it is very difficult to find out the steam spot because this is located in some part of reservoir. As you know, reservoir is located about 1 to 3 kilometer depth from the ground surface. Our challenge is how we can read the deep informations by using shallow drilling, such as we make very small needles and shallow needles. And using that surface manifestations and data using needle, that we try to interpret the deep reservoir conditions such as temperatures, the pressures, fluid amount, and the fluid flow. So at the first stage, supported by JICA and JST in the framework SATREPS. SATREPS is a very long name. The Science and Technology Research Partnership for Sustainable Development program from 2014 to 2021 year before that. So, and the subtitle is the bagus. That is very good in Indonesia. So that is meaning beneficial and advanced geothermal use systems. So this project is composed of 4 parts. The one is the steam spot detections is the main part. In addition, the remote sensing-based technology for environmental modeling and the numerical simulations, the reservoir and the power generation for long-term resource use. And one of the important things is human resource development for young researchers, engineers, and students. So at first, we made the conceptual model, what is a steam spot. We think the steam spot is an intersection of 4 elements. One is existence of continuous permeable fractures and young fluid, and high reservoir temperatures, dominance of deep origin, the cluster gases, the connections between near surface and reservoir by fractures and large steam amount, and the permeable presence of hydrothermally altered minerals and proof of gas and fluid ascent to the near surface. So maybe these fractures or fluid or the permeable zones can be detected, can be interpreted by several methods. For example, fracture analysis using satellite image, topographic data, and using multiple gas geothermometers and stable isotope or large isotope analysis, and terrestrial gas analysis using radon and mercury. To realize detections of a steam spot, the missions of this project is provision of new machines to Indonesia supported by JICA. So, for example, this fracture analysis provided for the radon measurement, mercury measurement, and HV mass, and cell machines and XRD like that. So in the ITB laboratory, you may have seen such new laboratory. So this figure shows a snapshot of our ideas. General environment and numerical simulations. So for the steam spot, the detections, there are the 8 subsections, the 8 items. The first one is the general fracture analysis using satellite image and the topographic data. And for example, the identifications of lineament and fractures. And the next one is that the radon mercury measurement using terrestrial gas and the gas component analysis, the traditional the gas components such as carbon dioxide, methane, argon, like that. And this one's mineralogical analysis that we want to find out the hydrothermal, the order the minerals produced by high temperatures, fluid flow interactions. And this one is that the chemical analysis of the geothermal fluid, and finally data integrations. So as I said, we have made small drill holes like that, and our challenge is how we can read the deep reservoir informations using shallow geological, geochemical, geophysical data. This side is remote sensing based, the emulator monitoring. This side is the numerical simulation based and the geothermal resource use for long-term power generation. So the outline of the detection of steam spot is like that. So at first, how we can find the continuous fractures. And the next step is using the fracture informations that we want to detect probably the zones of highly probable zones of fractures. And the next step is that remote sensing for specifying hydrothermal alteration minerals. And that we focus on the potential zones of ascending of the fluid and the steam. To detect such signatures, that we drill very shallow drill holes and the measure radon and mercury or traditional gas component. The next one is that the mineral analysis to make sure the hydrothermal altered the minerals, and water analysis to make sure deep origin gases. And finally, specifications of steam spot. The flow is like that. So the target area is around the Banton basins. At the first stage, 1 year wind, our main target, and the Patuha is included in our first stage, and now the second stage. And the northern part, Tampomas and Tangkuban Prahu are also our target area. So there are many outcomes, but I just introduced several important outcomes. One is fracture calculations of lineament, the extractions. Of course, we can use several sources of the remote sensing data or topographic data. And this is one examples of lineament detections using the shaded digital elevation model data. So that you can see the predominant fracture directions like this one, and some part are perpendicular, the two directions. And using borehole data and the geostatistics, we made some of the areas for the 3D fracture modeling, including strike and the deep. And interestingly, that the how many percentage of tip of production wells are located on estimated fractures. That we make sure that 77% of the tip of production wells are located on the estimated fracture planes. So that we think that our estimations is probably correct. So using this information, we made shallow drillings to make sure the ascent of the steam and the fluid. So this is maps of produced 25 shallow drilling wells, and using by hand and measure the radon. The considerations is like that. There are two types of basically radon. The one is stable, the decrease type. These are traditional. It means that there is no supply, continuous supply of gas. The other one is a stable patterns. It means that continuous support the radon gas. So we think this is the good places of the ascent pathways of the steam and fluid flow. And the targeting this the stable patterns, we analyze the mineral distributions using satellite image data. So in these figures, the red is the calcite, and green is aurinite, and the blue is the kaurinite. So for these stable patterns, we could make sure that hydrothermal alterations minerals are concentrated. So this is to prove the fractures and the presence of hydrothermal altered minerals. And by applying some geophysical method, of course, you know, the MT, AMT is a powerful tools to detect the resistivities to deeper part. So this figure is very interesting because the vertical continuous low resistivity zones are very clearly appeared. It means that there is a pathways of hydrothermal fluid, and this path the cause the anomaly patterns of radon. Now also that we made many geochemical analysis using waters and the gases, including the noble gas, the stable isotope, the radioactive isotope. This is one snapshot of distributions of the oxygen isotope and chloride distributions. And using this map, we interpret where is the parent fluid and where is the steam-rich zones. For the environmental monitoring or to detect geothermal the resource, high potential zones for geothermal resource, we use the base station information because in Indonesia, like Japan, most areas covered by thick vegetation. So it means that it is very difficult to get the surface geology, the mineral, the informations. So, but the vegetation had indirectly subsurface informations. So using the vegetation anomaly, we found out the relationship between the fractures it is interesting because the vegetation anomaly colored by red are long, the fractures. So we think that these fractures act as pathways of ascending flow. The next two examples of cluster deformations for the long-term geothermal resource use. So usually the method using such a satellite image, we say this is the difference in SAR. So the color means the deformations topography. So that you can see that this is a very discontinuous topography because of the high coherent part is very limited. But when we use the geostatistics to interpolate the no signal zones, that we can get very clearly the aerial deformations of topography. So in this figure, this one is subsided zones, and this one is uplift zones. So that we could make sure that this part is mostly the overlap with steam-dominated reservoir, and this part the fluid-dominated reservoir. And the final result is a potential map of the steam spot by integrating the geochemical and fracture data and the gas informations. So in this part, the red part means that high potential of a steam spot. And we verify that the tip of production well and the high potential zones of steam spot. And the correct answer rate is 71%. So among 34, the tip of production wells are located in 24 high potential zones. So this is not perfect, but we think that our method can be available to find out good prices of new geothermal power generation. So where is steam spot produced? This is a general map using integrations of geochemical data. So these white zones, the steam dominated zones, and this blue is the liquid dominated reservoir. So that fortunately, these locations showing high radon anomaly and fracture concentrated the portions and the steam spot, we could make sure that the exist included in the steam-rich zones of upper part of reservoir. So the fourth items of our research is the human resource development. We invite every 4 years the young ITB faculty members and engineers of company and ITB student to Kyoto University and do the fundamental and the applied lectures of geothermal science and technology, well testing, reservoir engineering, geothermal drilling, like that, and the laboratory experiment and the presentations and field work. So despite just 4 the years, we invite 54 in total trainers, ITB student, ITB staff, energy, Geodeepa energy, and CGR. This is a snapshot of our instructors. This is me, and this is a field work to the Hachover geothermal power plant. This is the largest power plant in Japan, located in Kyushu areas. So this year, the 1 year delay that we had World Geothermal Congress of World Geothermal Congress. This is the largest geothermal workshop, international congress. So that we presented 9 topics that this overall our project and fracture analysis and geophysics, geochemistry, and environmental monitoring and numerical simulations for long-term geothermal resource use. And this is also our project can be contribute to the human resource development. The many, not so many, but enough numbers of students got award for their researches, including Kyoto University and ITB. And we published 24 papers co-authored with ITB, including impact factors. And we present 48 the papers co-authored with ITB for international, including international conferences. And one examples of the published papers in like that. This is the highest level journal in the field of remote sensing, the remote sensing of environment. And for example, Geosamics is the flagship journal in the field of geothermal and applied geochemistry. So all ITB, the graduate, and our Kyoto University staffs and students. And we published the 10 in total, 9 or 10 newsletters, and for the many workshops in Kyoto University, and invite Professor Roland Holm from United States, and and we invite our collaborators, and that this is a snapshot of workshop in Hasanuddin universities. And I'm very pleased that for this project, I was awarded the ITB award and some contributions for Egyptian society. So now our project move to the second stage, the AXIS, the BAGUS project. The AXIS means accelerating social improvement for SDGs achievement. So the content of the project almost the same with the SATREP's BAGUS, but the difference is this one, the drilling survey, even though they're limited to 500 meter depths, but this must be important to make sure that our estimations of steam spot by making sure that presence of hydrothermal, all the minerals and high temperatures in the shallow depths. This one, as you, of course, you know that reservoir, actual reservoir located the 1.5 kilometer, 2 kilometer depths like that. So our data is limited just like that. But that we want to extrapolate our data to deeper part. So this one is the two side. But unfortunately, as you know, due to pandemic or COVID-19, from the start of this project, so nobody of Kyoto University side, Japanese side, succeeded in going to Indonesia. That we have continued to research collaborations using basically Zoom meeting. But with great help and cooperations of ITB and Energy, Geodepa and Energy and Siemens Icgere, field work and experiment that have been implemented by Indonesian team. And with the result of Satter's Bagus, this one published in Applied Geochemistry, that we made the conceptual model in Patuha. The next stage is Patuha. The previous stage target is 1 year wind. So our target is that stimulus zones in reservoir. So that maybe this is the inflows of the recharge areas, and this is the discharge. So using geochemical data, we made the conceptual model of fluid flow, and this is just the conceptual model using geochemical data. So we made sure that this conceptual model is correct, or some part need to be improved by using numerical simulations. So the numerical ideas of the fracture distributions, photo distributions. So using this logical map. So the sum of the fault, of course, you know, have a functions of permeable zones. Some the fault have a functions of impermeable zones. We consider such spatial heterogeneity of fault functions. This one is showing that the steam ratios, vapor ratios. So the upper part of reservoir, showing the vapor dominated zones. So using these informations and by making the potential map by integrations of the fracture data and some the geochemical data. So finally, we made two locations of drilling for 500 meter depth. This one, and by integrating other new data, this must be one of high potential zones for steam spot presence.
Sorry, Professor Koike, we have 5 minutes left.
Okay, thank you. The last two slides. So we are lucky because our the third project was accepted by the JSPS. So next one is a critical spot. So this one is that we have to try to find out steam spot to enhance the energy. Next our stage is the critical spot. It means that the near temperatures, pressures, the critical conditions, waters. So in Iceland or other world, the supercritical geothermal power generations is now the new topics. So we want to know that where it's the locations of critical spot. So now this is the table for our collaborations with ITB, by Satellabs and Axis, that we are starting here, almost half the stage. So the next stage is that we are going to the target, either 1 to 2 kilometers, 2 more, the deeper depths to find out steam spot. And the next one is a critical spot. But this one is some examples of our research result. And finally, thank you very much for support, Satellabs, Axis by JICA, GST, and our strong collaborations, Star Energy, Geothermal Energy, Siemens Icgere, and of course, collaborators for Indonesian side and Japanese side. Okay, thank you very much for your kind
thank you.
attendance and listening. Thank you very much.
Thank you very much, Professor Kaitsuaki Koike, for the excellent presentation. We have plenty questions in the Q&A box, but maybe we just try to answer it live for one of them. I will read you the question. Dear Professor, with the combination of fracture lineament analysis and fluid geochemistry isotope, could we interpret the source of the fluids? Do they come from geothermal itself or not? And related to uncertainty of near surface geochemical alignment data, how could we confidence the result? Could we reduce drilling risk? Okay, maybe you can answer that question. Thank you.
Yeah, okay, thank you very much. So we combined several kinds of geochemical data, such as traditional, the ion concentrations and the isotopes of stable isotopes and the radioisotopes, and the isotopes, for example, the helium, like that, and the source of the fluid can be interpreted. For example, the traditional is a stable isotope for both oxygen and hydrogen. So of course there is the typical the diagrams showing the relationship metric waters and the magnetic waters and the such the progress of magnetic waters and metric waters and upflows. So that the combinations is, I think, the indispensable. For our cases, that combination of stable isotope and the isotope analysis of strontium, and also the isotope analysis of carbon and nitrogen. So by these combinations, well, this is just estimations, but we could interpret that the source depth is the deep and source depth is shallow. For the case of the band of basins, is the northern part of band of basins, including Patuha, Takpan Prafu, maybe that the deep source, because that such isotope, the data that indicated that the mold and mantle the properties, but the southern part is shallow. And it is interesting that how we can reduce uncertainty. And the two reductions of uncertainty, they're also very effective by integrating the geochemical data. And the linear method data, just finding out that the pathways of the fluid flows. So the answer is that integrations is the best solution to reduce the risk and to find out and the fluid source depth. Thank you very much.
Okay, thank you very much, Professor Koike, for the answers. Maybe later, if you still have time, you could kindly answer the other questions in the Q&A box by typing in the box.
Yeah.
And thank you very much for your presentation and discussion. I think that conclude our first session. We would like to thank all the key speakers of the first session for their time and the knowledge they shared with us. And for the participants, we sincerely hope you enjoyed the first session of the conference. Thank you for your participation. And now I would like to give the stage back to Dr. David Sahara to give details about the next session. Thank you very much, everyone. Have a nice day.
Thank you very much, Dr. Taufik Hidayat, for hosting the first session of our conference. And on behalf of the committee, we would like also to thanks to Professor Nick Rolison, Professor Akbar Ramdhani, and also Professor Katsuaki Koike for giving a very insightful presentation to us. We would like to continue to the second session of the conference, in which we will have Mr. Bilal Aslam as the host of the second session. Mr. Bilal is a lecturer at the Petroleum Engineering of ITB. He finished his bachelor and master both at ITB, and since 2020 he became the lecturer in the Petroleum Engineering of ITB. without further ado, I would like to give the time and also the screen to Mr. Bilal Aslam to lead the second session of the conference. Please, Mr. Bilal Aslam. Okay, maybe there's a connection problem perhaps with Mas Bilal.
Yes, it seems Pak Bilal had a lost connection.
Mm-hmm.
Yeah, he has joined again.
Pak Bilal?
All right. I'm sorry. I think I have a connection trouble just now. So shall we proceed to our next session?
Yes, please.
Okay. And thank you, everyone. Let me introduce myself. My name is Bilal Maidika Aslam. I'm currently a lecturer, junior lecturer in Reservoir Engineering Group in Petroleum Engineering ITB. And I will be the moderator for our next session. So as per the schedule, we will begin the keynote speaker from our honorable speaker here. So is Professor Jian Zhao is available?
Yes, I'm here.
Okay, so I will introduce the first speaker for our keynote session. Wait, let me share the screen to show Professor Zhao profile. Okay, Professor Jian Zhao is currently a professor in Department of Civil Engineering in Monash University in Melbourne, Australia. And Professor Zhao completed his PhD in Engineering Rock Mechanics from Imperial College London, and currently he is the Vice President for Asia International Society for Rock Mechanics. And he is also ESRM Fellow and in International Society for Rock Mechanics in 2015. And currently he is also the Editor-in-Chief, Tunneling and Underground Space Technology from Elsevier Journal. His specialty is in rock mechanics. He has a lot of publications, mainly in the Journal of Rock Mechanics and Mining. So without further ado, I will let Professor Jian Zhao to have the floor. And for the audience here, if you have any question, please type in the Q&A box in below of your webinar screen. And after 30 minutes, I hope Professor Zhao will allocate his time to answer your question. So Professor Zhao, please, the floor is yours. Thank you so much.
Thank you. Thank you. Okay, let me share my screen as well. Microsoft. Okay. Share. Right. Now, are you able to see the PowerPoint?
Yes, very clear.
Okay. Right.
Could you please use in full screen, Professor?
Yeah, that's what I'm trying to do now. Okay, good. Is it okay? Right. Am I okay with that?
Yes, we can
Okay,
see
good.
your slides clearly.
Okay, good. Okay, now let me start with sort of okay. Thank you for the invitation to come to give a presentation here, and it's really a great pleasure to be here, and with the ITB, which one of the best universities, technical university in Indonesia, and I was asked to give this topic by your side. And it's very general. So talk about rock mechanics for tunneling or tunnel engineering. Now for rock tunneling, and basically we are looking at excavation and the support of a tunnel. So a tunnel is where you make a hole in the rock, and first, then to support the hole to be functional. And that's where the main function of tunneling is really excavation support. So my talk will also look at rock mechanics for excavation and the support. And just a quick brief introduction of the university where I come from. It's based in Melbourne, but with very many regional campuses and also international campuses. And one of the campus will be Indonesia in the very near future. I think they are now starting to build a campus in Indonesia. So you will see Monash University in Indonesia very soon. Okay, it's also a G4 University, GIT University, which is a research intensive university. It's a very multidisciplinary sort of a campus where engineering, science, basically everything, all the subjects. And the engineering school is probably also one of the largest in Australia. And we certainly have the largest rock mechanics group in Australia. We have about 10 faculty members plus 50 plus PhD students on rock mechanics alone. And we have probably the best rock mechanics laboratory in the world, most advanced. And we're covering construction, mining, and energy as well. So it's a very broad rock mechanics activities, and we're providing research as well consulting work to the industry. Now back to rock mechanics for rock tunneling, and start with rock excavation. Now when we talk about excavation, we are talking about try to remove rocks. That is what we are doing tunneling. So we try to remove the hard rocks, and primarily at the moment, the most common way to do it is either by a machine to excavate it or by blasting to break rocks. So their common methods are by TBMs or mining machines, which are mechanized tunneling, and we have by drill blasting, and also for soft rocks, we're doing with what we call the sequential excavation, which commonly known as the Nathan method. Now this is a TBM, a small TBM. You can see that the machine itself, the cutter is in the front, so the machine turns around and excavate the rock. So when the machine turns around, they push the cutter into rock and to basically grind the rock, to break a rock, to fracture rock. So you can see the fracture mechanics there. The rocks are being fractured and to be forming chip. And what you see in the front, the working rock face, nicely, it's a nice rock, granite in this case, you can see the patterns of cutter and roller cutters on the rock surface. Similar mechanism for load headers or miners, which also using the different cutters, but again, with impact loading, with rotations, you're basically biting into the rock and to fracture rock. So there's a lot of fracture mechanics involved with excavation part. And we do have a lot of rock mechanics involved with excavations. So rocks are fractured through impact loading, through excavation and the interaction between the cutters and the rocks. So you can see it is determined by the rock mechanics properties, plus other property like joint spacing, orientation, and the loading applied from the machine itself. So we have to understand the rock mechanics, rock fracture mechanics, and particularly associated with the probability, which is indexing for how easy rock can be cut by the machines. And in terms of overall performance of the machines, we also have to look at rock abrasivity and the cutter wear, which is also a property of rock material hardness. In the geological sense, it's about coarse content. The more coarse, the harder materials, the more wear, and therefore we have leading to slower excavation rate. And geoblast is where you basically drill a hole into the rock face, you put the explosive in the hole and blast away the rock. So this is typical what we do for geoblast. It is done in a cycle. So this is a typical illustration of what we call geoblast excavation cycle. So we start with drilling the holes into the rock face, charging explosions and put explosive in the holes and blast away. After that, you ventilating the air and you're scouring the endangered sort of pieces, then marking out the materials. And often we also have to secure the working phase by bolting and shotcreting. Then move on again to geoblast. We probably typically do 2 or 3 times, 3 rounds a day, depending. Basically about 6 to 8 hours one cycle. Now, again, there's a lot of mechanics involved with this drilling and blast excavation. We will drill the rocks, the mineralogies, abrasivities, and again, the interaction between the drill and the rock itself. And often is also, we have the term to be determined in terms of drilling rate index and also bit wear index. Rock fragmentation by blasting is even more complicated mechanics issues. And it's definitely involved with the rock strength and also involved with explosion mechanics. The mechanics between explosion, blasting, and the rock fragmentation is far complicated than typical common rock mechanics. It involves with dynamics and aerodynamics. So there are a lot of complications with explosions. And there are still a lot of research to be done and to understanding how to basically optimizing the explosive explosions and with blastings. And for soft rocks and for soft and poor rocks, what we do is we cannot making a tunnel in one go because of the ground is very poor, the ground will collapse. So therefore what they do is you do it to a sequential excavation, making a small section first, one by one, then open up the whole face. So this is what we do with the soft rocks. So this is what you see here, small sections. And typically you do it, say, a few small sections and to forming a large tunnel. And again, in this case, the rock mechanics for such excavation is not really the strength issue here. The strength is very poor already. So because of poor strength, you got a lot of deformation problems and stability problems. But again, you can see there's an issue of rock mechanics in terms of deformation, large displacement, and the collapsing due to the weakness of the rock mass itself. So again, there's a rock mechanics involved there. And so if you look at the whole issue there, in fact, the excavation method itself is determined by the rock mechanics, determined by the rock properties. For example, if you're looking at the lower to higher strength rocks, which is typically competent and or even weak with groundwater, then TBM can work very well. But if the ground is changing frequently and a mixed ground, and you try not to use TBM. So you can see TBM is only suited for certain rocks, ideally. And same for load header. If you are looking at very high strength rocks, and the load header is not going to work. Any rocks beyond 120 megapascal, the cut bits of the rock load header is not going to be working with such high strength, hard rocks. And it's not going to be very good in unstable ground and with groundwater. Similarly for geoblast, again, it works very well in extremely high strength rocks. So that's what blasting is most effective with hard rocks. But it has a problem with unstable ground. And as I mentioned earlier, sequential excavation is only for poor rocks. So you can see rock properties is a primary function of determining which method you use for tunneling, for excavation. Now, come to the rock support part. And there's a lot more rock mechanics involved in terms of designing, determining the rock support. The first thing I want to highlight to everybody is that if you look at rock itself is a strong material. It's typically stronger than any concrete. You hardly find rocks softer than concrete. A few of them, mudstone, shales, majority rocks are stronger than concrete. So therefore you don't want to support harder materials with concrete. So therefore what we do is we just try to use as much as possible rock as a structure material. That means you try to utilize rock as a self-supporting material. Now the only problem is rocks are broken and fractured. So therefore we use reinforcement to make the rocks to be stronger and continuous, therefore to be self-supporting. And rock support is also design is also based on, at the moment, empirical method, based on the cases has done before. So still in a way it's kind of an art rather than a science. We try to making rock design, support design to be a science, but unfortunately we're still not there yet. So there are a lot still going on to understand and particularly how the support and the rock mass are interacting. And but again, you can see rock designs are related to rock mechanics and also construction method, depending on which method you are excavating and so on. So therefore, for TBM, you use the different support if you are doing with geoblast, typically. We do use numeric modeling to predict and extrapolate, and we do use monitoring to verify design. So it's very important part of the construction as well, using monitoring. Now, here are a number of typical design methods for rock support. And the most common one is we're using what we call rock mass classification systems. Here, the most common ones are Q systems or the IMRs. We're trying to use, from there, we try to quantify the rock mass quality or rock mass strength and to design the support accordingly. And these are mainly for jointed rock mass, deal with sort of computations to helping us with special cases, such as very high stress, deal with bursting and spalling, deal with squeezing. And so therefore, there are a number of methods we are using, but still primarily the most common ones are the rock mass classification systems. Now here is an example of how the Q system are used for design. So typically we will have the rock mass quality assessed already through standard navigation, the Q values, which is the horizontal axis. Then if we know what is the size of the tunnel, the span, for example, on the vertical axis, then we can have the section where the dot is. So that's where I tell you what's supposed to select. Here tells you the shotcrete thickness, tells you the rock bolt's length, and tells you the rock bolt's spacing. So this is a typical chart for Q system, which is very easy to use. And then we use very often for rock tunnel supports and caverns as well, depending on the sizes. And currently, the largest span of the tunnels or caverns is 60 meters wide. And so that is also designed based on this particular chart. Now, as I say, we do use analysis to look at support, and particularly for soft rocks. So what we do is we use what we call the ground support interaction curves. So we try to analyze or anticipate what ground is going to move when after excavation. So the ground is going to be squeezing and moving, and then after, then we put in the support and try to then support we mobilize together with the ground. So eventually these two were in equilibrium. So that's where the dot point is. So once the ground's movement and the support movement or support pressure mobilized from support from the movement is in equilibrium, then we have the tunnel stabilized. Tunnel will not further move. So therefore, it's basically being stable. So this is what we try to achieve. Try to achieve such equilibrium through understanding the ground movement and also the support element properties. And we also use numerical modeling, as I say, to helping us to extrapolating or to verify design. And you can use FEM, final element cleaning method. Most cases we do use that. This is particularly good for general deformation, for soft ground, and for look at the overall deformation and the support in general. But if we have a blocky rock, if we worry about rocks are falling down block by block, if we look at the failure along existing joints or fractures, and then we can use what they call DEM, the discontinuous method, to simulating the actual failure due to all those discontinuities. And so both are used, in fact, and depending on the complications and the situations. And we do use even 3D DEM to model some of the cases, particularly with the failure cases, which if we want to understand exactly how the tunnel fails. Now we have a number of methods used for rock support, but as I mentioned earlier, as rocks are stronger, so what we do is we tend to use reinforcement rather than support. Reinforcement is really a reinforcement. They're not providing as active support. So what we do is we have steel bars typically inserted into rock to make rock to be continuous through the reinforcement. So therefore, you primarily improve the continuity and also having the bar through the joints. So therefore, your joint is no longer able to move. So therefore, the block are not able to move. Those are typically done by rock bolts and sometimes can be by cables if the lengths are required. And also use shotcrete as a reinforcement, and which is a thin layer of concrete spread to the rock surface. Rock support is really providing the reactive force to the opening around the tunnel. So this is the element installed additionally to countermeasure the deformations. Therefore, it's really pushing back the ground. And typically we're using pillars and also use steel sets or using concrete lining. All those are being sort of is an active external element to be providing support to the ground. Are there rock mechanics? Yes, there's really the essential of rock mechanics being used for design such element. For example, if we look at individual blocks falling down, and we have to identify the key blocks and to secure the key blocks. And in fact, in the, I think the 80s, since the 80s, there is a subject called the key block theory within the rock mechanics subject. So this is one of the sort of area developed to identify the key blocks and to secure the key blocks. And if you're using the both to providing a formation of rock arch, as we shown at the lower diagram, or to limiting the shear, or to improve rock mass, again, we have to look at how the rock mass are being enhanced or being improved, and what is the new improved rock mass strength. Again, those are all subject of rock mechanics. Shotcreting is something which we, as I was saying, just spreading the concrete on the rock surface, but it's a very thin, so therefore it's not really a structure layer to be thick enough to be as a concrete structure, but it is very effective in terms of reinforced rock because the concrete covers the surface and also goes into the fractures. By going to fracture, the blocks or rock locks the blocks. So therefore it's very effective to preventing small blocks to falling down. So that's why often we use rock bolts with shotcrete that couple together. The rock bolts deals with locking down the large blocks. The shotcrete is securing the small blocks all together. And in terms of rock support, the pillars are really there to carry the overburden load. So we have the loading from the roof, from the above overburden. These are carried by pillars. So you have to look at the pillar loading analysis and the pillar strengths. And if we're using the pillars, particularly for within the sort of natural pillars, using existing rock, like the lone pillar in the mining, and so there's a lot of rock mechanics to be involved to analyzing the strength of a pillar, the stability of a pillar, and how the pillar will fail, and how the rock joints will be interfering or will affecting the strength of rock. So you have different failure mechanisms, as we're seeing here in the diagram here. So again, you can see rock mechanics for pillar support. And if you look at the rock mechanics for steel sets and the concrete lining, and again, there is an interaction between the support and the ground movement. As I mentioned earlier, if the ground does not move, the support is not providing any pressure. So the pressure is reacting pressure when the ground is moving in. So the ring actually against the movement. So therefore, there is a interaction between the ground and the support. Right? So it's providing the support pressure to the rocks around the tunnel and limiting the tunnel to deformation. Now tell me, are there mechanics there? Certainly is. There's mechanics problems, right? And the support is also, of course, the line is also providing support to or constraint towards the ground to water inflow, which is a minor issue. If we talk about the strength and the support, is the primary to limiting the ground movement. And if you look at the design of the Q system, for example, if you look carefully, you can easily identify different zones. Now, if you look at the red zones and the pink zone, the purple zones and the blue zones, you can see they differentiate very clearly. So one zone is look at, for example, the blue zones. It's really deals with localized block failure, where you're only applying rock reinforcements of bolting. Because this area is where the rock mass quality tend to be good, and the jointings are a bit wider. So therefore, the major failure is block falling, sliding. So therefore, you're using rock bolts to support. At the same time, if you look at the middle part, this is generally much worse rock mass, but same time, still more or less sort of a general failure. So therefore, you use sort of a reinforcement together with shotcrete to secure the area. But when you move to the red zone, that is due with squeezing, bursting, general failure, the weaker rock. Therefore, you're using steel ribs and the concrete lining to do that. So you can see the different mechanism, different support to deal with different rock failure mechanism and deal with different rock strengths as well. So they do have different behavior with different rock mass strengths. So different behavior leads you to decide with different rock support. Now here is a sort of a generalized illustration of how the support is working with the rock mass strength and also with the stress. So the horizontal axis is the strength, which is based on GSI. The vertical axis is the stress, which is the depth. So you can see at a lower stress level, at very high strength, you don't worry. You have no support or little support of individual bolting. But if you're moving towards lower strength to the right, then you can see support increasing more and more from little bolting, more bolting, and then towards concrete lining. But it's also affected by the strength, the stress. If the stress is higher, you start seeing spotting and start seeing sweating. So therefore, you have more general failure. You have more support to be installed. So this is what you have sort of a generalized picture of how support is associated with failure mechanism, associated with different strengths and different stress
Sorry, Professor, you have 5 minutes left.
Okay, this last slide, in fact, this is the last slide, so I'm finish up. So by finish up this talk, so what I wanted to highlight is, again, there's a lot of application of local mechanics to tunneling. Local mechanics deciding together with, of course, other subjects like Indian geology, like construction method, but together they help to design the layout and the geometry in terms of depths, separation, and routes as well. And as I mentioned earlier, it definitely deciding the rock excavation method. So if you do use a TVM or using blasting, it's all depending on the rock mass properties. Designing the rock support is based on the rock quality and rock mechanics. So again, we have mentioned already. It also helps us to managing the risk and hazard. For example, one of subjects which we are working on very closely is to deal with earthquake effects on tunnel stability. And again, we have not have any real code of design yet, how we design the guidelines for tunnel on this high intensity earthquakes. Again, that is something, again, that's a subject we are now intensively investing and try to understand it. And of course, helps to design the environment and sustainability. I think this is all what I gonna talk. As I say, this is a general topic as was given, and again, by all means, ask any questions specifically, and I'm happy to answer. And thank you.
Thank you so much for your comprehensive and very interesting presentation in rock mechanics for tunnel engineering, Professor Jian Zhao. And we do have several questions here in the chat box. First question is from Mr. Nuhindro Priyagung. So Professor Jian Zhao, a probability of failure gives information the percentage of safety factor that the value fall below a certain stable safety factor. So how to use the information, for example, to estimate the unstable condition from the information of POF? Thank you very much.
Well, at the moment, what we have for design is all based on what we call the successful cases. So if you look at the Q chart, all the chart, if you design according to the chart, you should not have failure. So at the moment, if you look at the rock tunnelings, there isn't a method to define factor of safety. This is another issue which now we are working on. Should we have a factor of safety for tunneling? And how conservatively so far we are designing the rock tunnels. And my comment is that we are currently designing the tunnels in a very empirical way and with very much over safety way. And so I can't really tell you and how we're going to working out the factor of safety so far issue yet. But it's probably, if you look at the structures, they have factor of safety. But because they know exactly the loading, they know exactly the strength. And in rock tunneling, those are all very much uncertainties there. And so therefore, we are over-designed a lot. In fact, I have a case which I just did for a cavern, and believe it or not, 70% of the boats has no loading at all. So that means the boats put in there, 70% are not even working. But you have to do it because the design guy tells you. Even those working only take up to 25% of the actual loading of the yielding strength. So you can see how conservative we are, but that's the current situation. So that's another thing that we have to do to improving such design by understanding more rock mechanics, by understanding the actual science and engineering rather than art alone.
Okay, thank you, Professor. I think that sums up the answer very well. So I'm sorry, there are actually several questions here in the chat box. If Professor Jian Zhao is still available with us, you may answer the question by typing. Okay. And thank you so much for your time and from sharing your knowledge and experience in this line of research. Thank you, Professor Zhao. And now we will move on to our next keynote speech, which the topic is coupled hydromechanics of fractured rock mass, which will be delivered by Professor Ki Bok Min from Seoul National University. So I think Professor Min is already available here with us. Okay, yeah, I'm sorry, Professor. May I introduce you first to the audience? Okay, can you stop your share screen a little bit? Thank you. Okay, and okay, Professor Ki Bok Min is currently a professor in the Department of Energy Resources Engineering from Seoul National University. He completed his PhD in Engineering Geology in KTH Royal Institute of Technology in 2004. And he was also an assistant professor in University of Adelaide School of Civil, Environmental and Mining Engineering in Adelaide, Australia in 2008 and 2009. And Professor Min already has a lot of published papers, peer-reviewed papers in journals, also in rock mechanics. So without further ado, I will let Professor Min to deliver his presentation. Thank you.
All right, thank you. Let's see. All right, thank you. My name is Ki Bok Min from Seoul National University, and it is my great honor and pleasure to deliver a keynote speech in this conference. And thank you, Rido, for the invitation. And Professor Asset, nice to see you again here. I'll talk about the coupled hydromechanics in fractured rock, focusing on its importance and also a few notable applications. So this is a legal disclaimer. And also, before I start the presentation, I would like to thank my former and current students who actually did most of the work presented in this talk. This was the picture before the Corona era, actually. I missed this event. This is an outline. I'd like to start with the fundamentals of coupled hydromechanics, and I'll focus on two relevant applications. One is geothermal, another is a geological repository for nuclear waste. I'll briefly touch upon this underground storage of CO2 before I conclude. So in many rock types, fractures are main conduits for fluid flow and deformation. This is a picture that I took from Sweden. And its understanding is important for both conventional applications such as mining or fractured oil reservoir, or emerging applications that I mentioned before. So the key observation is that the fracture actually deforms with the action of stress, and then the permeability and hydraulic behavior changes. And the fact that the fractures are stress dependent and deformable in either elastic or plastic manner is both an opportunity and challenge for us. And if you think of the source of the change in fracture, this can be an excavation or thermal loading or hydraulic pressure or seismic loading, to mention a few, depending upon applications. And this stress-dependent fluid flow can occur in a single fracture, as you see here, or in a block scale, as you see here. And this has a great implication for many applications. And these graphs are results of a coupled normal and shear flow test on granite. That the test was conducted in SNU. And this shows that fractures are really stress dependent, and the change can be significant. Under the normal loading, there was a change of permeability about 1 order. And during the shear loading, there was a permeability change of about 2 order. So there can be a big differences in the hydraulic behavior subject to the mechanical normal or shear loading. So that's why we need to consider these fundamental phenomena. And actually, in terms of shear shear flow, shear dilation is the main mechanism of permeability change due to shear stress, and it is its main parameter is a shear dilation angle. Dilation angle is a arctangent of the ratio of normal opening and shear displacement, and it is in the order of 14.7 or 3 degree, depending upon the normal loading, according to the test conducted in Sweden. And as change of aperture is by in the order of tens of hundreds of micron, that's very important for the fluid flow. And also this dilation angle is also very much a function of a normal stress, as you see here. And I'll get back to this topic later. And let's have a look at the block scale instead of a single fracture. And this is a study that I did for my PhD a long time ago. And I generated a fractured rock in the size of 5 meter by 5 meter with a discrete fracture network inside. And I then carried out numerical experiment by discrete element code by alternating mechanical test and permeability test. And this is the plot of permeability with respect to the stress ratio of horizontal to vertical stress. And I was able to see an abrupt permeability change when shear slip occurred. And the increase of permeability was by the factor of 5. And this phenomenon is more dramatically shown by looking at the fluid flow change in horizontal and vertical direction. So this result shows that the stress-dependent fluid flow is real, can happen in a block scale. So actually this stress-induced fluid flow, as I mentioned before, it pose both challenge and opportunity in different engineering. In enhanced geothermal systems, we actually want this kind of thing to happen. And this is actually exactly mechanism of hydro shearing and also actually induced seismicity. So we want this to happen in a controlled manner by avoiding large induced seismicity. However, in CO2 geosequestration, this is something you want to avoid because this shearing can induce the leakage of CO2 and possibly induce seismicity. And also nuclear waste repository, this kind of phenomenon has not received the due attention, but excavation damage zone, or thermal stress, or earthquake can possibly induce this kind of aperture change, the gap of a fracture, and this is something that you want to avoid. Therefore, I argue here, coupled hydrodynamics in fractured rock is important for many applications. So let me start with the geothermal energy first. So geothermal energy is an attractive renewable energy. And because of its ability to offer base load power, and in the world, we currently have about 16 gigawatts of installed capacity. And Indonesia is in the second place in the world. And on the other hand, unfortunately, Korea does not have a geothermal power yet. So the problem about geothermal is it's being currently used by only some part of the world without becoming a universal energy. So in order for geothermal to be a universal option, people say this kind of enhanced geothermal system is necessary. In this system, we go deeper and you try to improve the permeability by hydraulic stimulation. So hydraulic stimulation is a key component for enhanced geothermal systems. This has a long history, has been tested for nearly half a century, and we still have a very limited success. And it depends on how we define EGS, but if we define new development in crystalline formation, a lot of past efforts actually turned out to have failed. Only efforts in France have succeeded. And even if the other efforts failed, although we have some notable scientific achievement. In talking about EGS, I'd like to introduce Pohang EGS project in Korea. And the site geology is composed of granitic gneiss in the target reservoir. And there are 2 boreholes deeper than 4 kilometers here. And a total of 5 stimulations was conducted. The temperature was about 440. And after 5 hydraulic stimulations, 2 months after the last stimulation, actually the earthquake in the magnitude of 5.4 was occurred. And therefore the project was stopped. And the rock core was extracted at 4.4 kilometers, and this shows numerous fractures, and system is dominated by these fractures, even at more than 4 kilometers deep. Therefore, the fractures in the deep reservoir is the main conduit for fluid flow. And the number of fractures was nearly 10 per meter. And a lot of different rock mechanics tests was carried out here in SNU, as you see here. This is the timeline of hydraulic stimulation and seismicity. And all of this happened in the course of 2 years, in 2016 and 2017. And hydraulic stimulation was carried out alternately in 2 different boreholes, PX2, PX1, PX2, PX1, and again, PX2. And the maximum induced seismicity during the stimulation was in the order of 1.7 to up to 3.1. But then after finishing this last stimulation, 2 months after, the earthquake with a magnitude of 5.4 occurred. And the government commission was formed right after the earthquake, which is composed of domestic and international experts. And after a year-long study, they concluded that the 5.4 earthquake was triggered by the hydraulic stimulation activity. And this conclusion was based on spatial proximity of the earthquake, which is only a few hundred meters away from the borehole, and also spatial temporal proximity of induced seismicity during hydraulic stimulations. And with this background, I'd like to talk about some outstanding technical issues about the EGS, which is closely related to hydromechanics, coupled hydromechanics. A report by US DOE summarized 5 outstanding technical issues like this. And some of this is quite closely related to hydromechanics. Therefore, I'd like to explain this one by one, especially in terms of drilling and reservoir creation and induced seismicity. Drilling is, it's expensive, and according to some data, in order to drill a 5-kilometer borehole, it takes in the order of $10 million. That's expensive, and a lot of people are working on this. But apart from this issue of economy, I'd like to point out one more important issue related to drilling in terms of hydromechanics. And this is a graph of injection rate and wellhead pressure observed in 2 different boreholes that is only 600 meters apart. But the responses in 2 boreholes, PX1 and PX2, were very different. PX1 has has a higher injectivity with it can achieve some injection rate with much less hydraulic pressure, but in PX2 we need a much higher pressure. And the reason for this big discrepancy is that the loss circulation material used during drilling to handle the loss of mud have blocked the borehole in PX2. Therefore, permeability damage occurred in PX2. And therefore, this kind of result shows that drilling and hydraulic stimulation really has to be integrated even during the stage of drilling. And regarding the reservoir creation, and it's important to note that there is no guarantee that you can achieve expected permeability through hydraulic stimulation. This is the graph in Cooper Basin in Jolokia in Australia. The data shows that the flow rate was only in the matter of 1.5 liters per second, even with very hydraulic pressure. It shows that hydraulic pressure, therefore this reservoir creation is not guaranteed. And similar observation was also found in Pohang. This is the data expressed in terms of equivalent aperture. You can interpret this as a permeability or transmissivity versus wellhead pressure. And with increased wellhead pressure, we can have a larger aperture, as you see here. The problem is when we reduce the pressure back, actually this just recovered. And when we talk about hydraulic stimulation, ideally we want to achieve the permanent increase of permeability, and we don't want the permeability to reverse back. But this was exactly what we saw here. And when you continued with the second stimulation, again, we saw the similar trend. Therefore, in case of Pohang, we could achieve a higher permeability, but this was only reversible, and permanent, irreversible increase of permeability was not achieved in Pohang. And also in terms of reservoir creation, this is the plot of a fracture pressure versus injection rate. And in another borehole, PX1, the increase of permeability was better. But if you look at the actual pressure curve, you could see a very, very clear phenomena of hydraulic shearing. However, if you look at the actual extent of injectivity, that was not as much as you expected. Increase of injectivity was in the order of a few times, and ideally you want to achieve an order of increase of permeability. I thought about the reason for this, and this may has to do with decreased dilation angle at the higher normal stress, and there are numerous tests of a dilation test under various normal load. However, the magnitude of load was limited to only 30 megapascal. But if you think of geothermal engineering, deep geothermal engineering, it's in the order of 100 MPa. And I guess the dilation angle at this high normal stress may be much lower than this. And this could be explained, this can explain the low permeability increase. And actually, there are no data laboratory tests that do the dilation test under this high normal stress. And I think we urgently need more experiment to confirm the shear dilation performance at high applied normal stress. And induced seismicity is, of course, a prime concern, and is of particular concern is induced seismicity during shut-in. High induced seismicity occur even after we shut in. And this kind of phenomenon was observed in Basel in Switzerland. And they had induced seismicity of 3.4, 5 hours after shut-in. And similar induced seismicity was observed during shut-in in Pohang. And here the blue is the seismicity during stimulation, and red is the induced seismicity during shut-in. We tend to have a larger and more seismicity during shut-in. And although there are several candidate mechanisms suggested to explain this kind of thing, still it is counterintuitive why even the increased induced seismicity occur after we start injection. And we need more research on this regard. And this kind of delayed induced seismicity during shut-in was consistently observed in the first 3 stimulations in Pohang. It was 84 hours after shut-in, 28 hours, and 15 hours after shut-in when we saw the large induced seismicity. I think this kind of induced seismicity is, of course, related to the interactions of coupled hydraulic, mechanical, and possibly thermal processes in fracture, and we need a better model to explain this. And these are the compiled data of delayed seismicity during shut-in worldwide. And as you see here, there are many data that shows this is the elapsed time after shut-in and the magnitude of RSK. And starting point is the magnitude before shut-in, and this is actually the magnitude of after shut-in. So therefore, there are consistently many data that shows increase of seismicity during shut-in, but they are in the order of 100 hours, or the longest delay was in Denver. It was nearly a year. However, all of these, the jump was mostly less than in the order of 1 in terms of magnitude. But in Pohang, the magnitude jump was from 3.1 to 5.4, large jump occurred. And this is very frustrating who want to control the induced seismicity during shut-in, during the hydraulic stimulation. And I think this is a big challenge. And another challenge is injected volume in Pohang was about in the order of 10,000 tons. That's very small. And in the past, the existing theory could not explain this big earthquake. And that's another actually challenge people need to explain. All right, so this was about the geothermal related to hydromechanics. Now I'd like to change the subject to nuclear energy. The 10% of the world electricity is provided by nuclear power, and it is 30% in Korea. And I heard there is no nuclear power plant in Indonesia. So situation about the geothermal and nuclear power is quite interesting in Indonesia and in Korea, actually. And one of the biggest problems for nuclear energy is handling spent fuel, which continues to be radioactive for tens of thousands years after operation. That is a big concern. And one promising option is to putting the spent fuel in deep underground. And many countries are considering this kind of option, and many people are working on this. And the concept typically known as KBS3, developed in Sweden, is used, and they have some engineered barrier like canister and bentonite, but the final retardation is through the natural rock. They assume the natural rock is not permeable enough so that the radionuclide can reach in the surface. And compared to other underground facilities such as mining, geological repository is different in that heat is generated from the spent fuel. Therefore, we need to consider thermal analysis. And we can think of a few important scenarios when you consider geological repository, like a thermal loading or some glacial loading or earthquake loading. But if you focus on thermal loading, due to temperature rise, thermal stress is generated, and due to some boundary condition that in the surface is open, therefore the thermal stress generated is predominantly in horizontal direction. And therefore, if in terms of Mohr circle, it changes like this from the red dotted line. Therefore, it has a more possibility to induce a slip due to this thermal stress change. And I termed this as a thermal shearing. And this kind of phenomena can be important for geological repository because the shearing can actually increase the permeability, and that's not good for repository. And thermal shearing itself is also similar to kind of induced seismicity. Therefore, this is also something we want to avoid, and we need to understand more. And I did a very simple modeling in the past, and this modeling shows the thermal stress generated around the repository is in the order of 20 MPa. And that usually occur, the peak is about at 100 years. And in the surface, there is a tensile stress at about 1,000 years. And as I explained, there is a more possibility of a thermal shear slip due to thermal stress about 100 years. And also,
Professor, you have 5 minutes left.
Okay.
Thank you.
Okay, there's a range of possible shear slip, and this can be investigated. Again, after 100 years, you can see a larger possibility of a shear slip in the fractures. And the amount of a shear slip can be also investigated by more explicit modeling of discrete fracture network. And this is a model that was just finished by my PhD student. And it shows that actually this temperature rise and transmissivity is a kind of permeability change. So temperature rise can be recovered. However, once fracture is slipped, it's a permanent change. Therefore, it does not recover to the initial stage. And this change can have an impact for the performance of a geological repository. And the third issue is about the storage of CO2. But I just want to mention that for CO2 storage, if you inject a large amount of CO2, again, in the cap rock, we are worried about the slip of a fracture here. And then this is a leakage of CO2. We don't want that. And also induced seismicity could occur. And that's something we need to be careful and we need to understand. And this is a well-known issue. And there are many papers dealing with this. And in my group, we developed a code called TUF UDEC, linking two code, and try to model the injection-induced shear slip by linking two codes. So briefly mentioned, and as you see here, the shear slip induced by this injected CO2 can be modeled by this code. This is an example. All right, so this is, I would like to conclude. And the coupled hydromechanics of fracture is of prime interest of many geological applications for example, for mitigation of climate change. And I argue here more fundamental research is necessary. For example, the dilation behavior at high normal stress. In terms of geothermal, especially for enhanced geothermal system, I want to emphasize that geothermal energy is essentially a hydrogeothermal energy. And we need to place more emphasis on hydraulics and coupled hydromechanics, because this somehow implies geothermal is about just the temperature, but no geothermal project stopped due to low temperature, but mainly they stopped because of low permeability. Therefore, we may call this hydrogeothermal energy. And there are a few issues that we need to study, that is delay the earthquake or the magnitude versus injected volume. There is some enigmatic behavior we need to understand. And in terms of hydraulic stimulation, the permeability increase was not guaranteed, and there was some insufficient permeability increase, and it was not irreversible. And geological repository, there was some issue, and CO2 storage as well. Actually, this is the last final advertisement. In my department, SNU, we are looking for students and postdoc and actually visiting professors to support. And the area is all fields of energy resources engineering, geomechanics, mining, petroleum, and geothermal, geophysics. We plan to support up to 10 young people by 2030. And the opening is actually open immediately. So if you are interested, please consider this opportunity, and you may contact me for possible opportunities. All right. Thank you for listening. Thank you.
Thank you so much, Professor Bin, for your very interesting and comprehensive presentation on coupled hydromechanics of fractured rock mass. And also, we also have some opportunities here presented by professors. I think it's a very interesting opportunities. And yeah, we do have one question here, Professor. So in the Pohang enhanced geothermal system case, is refracturing is considered as a possible mitigation when the pressure is depleted to enhance the permeability?
I couldn't hear your question. Where can I see in the chatting or?
I'm sorry, Professor. That was my question. Actually, yeah.
Okay. Yeah.
Yeah, my own question. So yeah.
Your own question. All right.
Yeah.
Could you repeat again? Sorry. Yeah.
Yeah. Yeah. I was interested in the enhanced geothermal system case because it shares similarity with the oil field development, where when the stimulation is it's not very effective again, sometimes we do refracturing. So we do refracturing. Is that a possibility in this enhanced geothermal system case?
Yes, because sufficient permeability was not achieved in one borehole. The stimulation was repeated 2 times. In another borehole, it was repeated for 3 times. But still, before the project was finished, still we could not achieve a sufficient increase of permeability. Yes, to answer your question, yeah, we did try to re-stimulate.
Okay. And yeah, we also have a question here from Mr. Nuhindro Priyagung. So Professor Kibokmin, in Pohang, how far the area of influence of the seismic? Thank you very much.
in terms of damage, it was much larger, but the seismic cloud was in the order of about kilometer scale, less than 1 kilometer, mainly focused on this. And the 5.4 earthquake was actually between two boreholes, so nearly it was in the site.
Okay, thank you. I think that sum up the answer from Professor Min. And I think that's all for
I have one question, Bila.
Okay, Professor Rido, could you please give your question?
Kibok, you have a very good achievement in hydro mechanic, a couple hydromechanics. In your opinion, what do you think about some people say hydrothermal mechanics? So put another variable in the model, thermal variable. Would it be possible in the future to do hydrothermal mechanics?
Oh, yeah, so depending on application, all three are somehow linked. So the example that I showed for geological repository, the source of a mechanical change was thermal. Therefore, thermo-hydromechanical analysis was necessary. And also for geothermal, we can stimulate hydraulically, and also thermally we can stimulate, because when you inject a cooler fluid, the rock fracture tend to contract. Then you can also have a larger aperture, and we can improve the permeability. That is also quite extensively considered in other areas, in the US, for example.
Okay, thank you.
Okay, thank you for your question, Professor Rido, and for the answer, Professor Min. I think that concludes the keynote session for Professor Min. And now we will move on to our final keynote session speech by Professor Wisub Bey from Sejong University. And the topic is Enhanced Oil Recovery Implementation Partnership. So Professor Wisub Bey is already available here with us, and let me introduce Professor Wisub Bey to all the audience here before he start the presentation. So Professor Wisub Bey is currently a professor in Department of Energy and Mineral Resources Engineering. And he completed his PhD from the University of Texas at Austin, and also for the master's study also in the University of Texas at Austin. And he has a lot of publication here in enhanced oil recovery and also geothermal and hydraulic fracturing stimulation. Professor Wisub Bey is also has done a lot of EOR implementation partnership with our colleague here, Professor Asep Kurnia Permadi. So without further ado, I will let Professor Wisub Bey to start his presentations. So Professor Bey, the floor is yours.
Okay. Okay. It's very nice to see my old friend, Professor Asep, Professor Neni, and I feel like I'm in before pandemic. Last 2 years, all the people in the world are shut in their homeland, and hopefully we finish pandemic soon and we'll meet again. And I was very happy to get the invitation from ITB, Professor Asep, but EOR implementation partnership, because, okay, can you see my slide?
I'm sorry, Professor, not yet. Could you use the share screen button?
Okay. Okay, how about now?
we still cannot see your slide, I think. If you have any technical trouble, you can also send the slides to me and I will show it to the audience. Oh yeah, it's starting. Yeah, it's starting.
Okay,
yeah, so
okay, good.
now we can see your slide already.
Mm-hmm. When oil price was higher than $100 US, our government support a lot to the universities and research centers and companies to go overseas to develop oil and gas and natural resources. And in Korea, in domestic land, we don't have any oil and gas field. So I was trying to find some kind of pilot plant, and I was so lucky to get acquainted with Professor Asep, and he gave us full support to cooperate with Indonesian oil companies. So I have pilot plant in Sukaranti field and the Merah field, and we cooperate and we develop several techniques about EOR, especially chemical EOR. And I'm so lucky, and I try to introduce some of EOR implementation partnerships. So introduction and some of basic EOR theory, and especially chemical EOR, and Sejong Lab introduction and partnerships. And enhanced oil recovery, and Dr. Larry Lake, he's the frontier, he's a pioneer of EOR, and he defined EOR is oil recovery by the injection of materials not normally present in the reservoir. That means not normally present in the reservoir means usually water and gas. So EOR process.
I'm sorry, Professor Bay. Could you use a slideshow so that we can see your slide better? So it's already shown, but yeah, if you use slideshow, it will be full screen.
So you can see my slide, right?
Yeah, we can see, but it's look very small. Can you use slideshow?
Slideshow.
Yes, I think in the bottom right.
Mm-hmm.
Or yeah, you can use F5. Press F5 maybe.
F5. Okay. That's better.
Yeah. I don't know why it's in presenter mode. Yeah. You use swap the presenter to the slide.
That's better.
Yeah, it's better.
Yeah.
Okay. Okay, how about that?
Yeah.
It's good.
Okay, so EOR is differentiated by IOR. IOR has various range. Usually primary recovery is produced by natural drive mechanism, usually high pressure of reservoir. And secondary recovery is gas and water injection, usually located in the reservoir itself. And the tertiary is any technique after secondary recovery. And he's Dr. Lake, and he's my professor, and I met him on an SP meeting somewhere in the US. And this is Duri field. I was luckily get picture from airplane. And this is Petropala in UPN in Yogyakarta. Now he's Professor Suranto in UPN. And he was my PhD student many years ago. And we visited Yogyakarta and we went Mount Merapi. Very, very impressive trip. And this young man guided me to 3,000 meters of Mount Merapi. And I met during the trip, I met these lovely children, and it was so impressive. And she's old sister, and tried to talk something to me, and I mean, that was so nice picture. And that picture was one of engineers, the photo from Dewey Field engineers. And at that time, year 2007, look at this million, 10 billion, 100 billion, million, 10 million, 100 million, 4 billion barrels. And that was year 2007. And this is Minas oil field, but still they recover only 50%. So they are looking for some kind of EOR process. Until then, they were pumping water, pumping big volume of water, and it was so noisy. And look at the young face of Professor Sepp. And the same, about 10 years ago, we were so young, and that durian was so so stinky, but the taste was really good. And we had MOU, and it was introduced in local newspaper. And also Mount Merapi, every several years they have eruptions, and these volcanic acids were so I mean, I was surprised. You know, this every 3-4 years, Mount Merapi, it erupted, and the sediment of those acids shows that kind of those pictures. And it was good memory that I had cooperation with ITB and the international companies. So basic EOR theory. The target is to minimize residual oil saturation. So high oil viscosity, interfacial force, reservoir heterogeneity is big obstacles. We have to solve these problems. How we can solve it? To mobilize residual oil, we have to enhance displacement efficiency and sweep efficiency. And displacement efficiency, we have to lower water oil surface tensions. So we use surfactants such as just like soap. When we have oil in the palm, we use a soap, then we can get rid of oil. Likewise, when we have oil, residual oil in the reservoir, we can use soap, then we can produce much more oil. And next, we improve sweep efficiency. So when we inject water to the oil field, we can just bypass it. We have to sweep much wider region. How we can do it? We can use high viscous material such as polymer. And sometimes we have channeling, then we block this channel, then water can sweep much wider. So we can use several chemicals to have better productions. Okay, so the goal of EOR is this enhance displacement efficiency and enhance sweep efficiency. How we can do it? In order to decrease oil viscosity, we apply thermal. We inject steam. And the largest thermal project in the world is Dewey Field in Sumatra. And reduce capillary force. And we use chemical or miscible method. We inject CO2 gas and other hydrocarbon gases. And when we inject sweep efficiency, we inject polymer, and polymer gives high mobility. This is very basic things. So EOR method will be 3 major methods. First is miscible, second thermal, several method, and chemical method. And four major important forces in fluid flow is viscous force, gravity force, capillary force, diffusion forces. We change these four forces to get maximum oil productions. Okay, for example, mobility ratio. Mobility is, when mobility ratio is high, then we have viscous fingering like that. When we have favorable mobility, we have this piston-like displacement. What we want is that kind of displacement. Okay, so when we decide the EOR method, we have to consider reservoir, rock, and fluid. Okay, I briefly introduce about chemical method. First, surfactant flooding. Okay. Likewise, when I explained earlier, usually interfacial tension between oil and water is 25 to 50 dyne per centimeter. But when we mix a little bit of surfactant, we can drastically reduce surfactant IFT up to 0.0 to 0.01 dyne per centimeter. So it gives this capillary number okay, this x-axis is capillary number and y-axis is SOR. So we would like to reduce this SOR. So this capillary number in water flooding is about this level, 10 to the minus 8. But when we mix a little bit of surfactant, not that much, little bit of surfactant, then drastically increase order of 10 to the minus 8 to 10 to the minus 5, 10 to the minus 6. So this SOR, residual oil saturation, will be dropping a lot, 100% to 70, 80, 90%. But this surfactant flooding has problems. This capillary number ranges only partial displacement of water flooding residual oil. Why? Surfactant, when we inject surfactant, are strongly absorbed on reservoir rock. So we inject valuable, expensive surfactant, but lots of surfactant are absorbed on the surface of rock or interface of oil and water. Then how we can improve this problem? Residual and another problem, when residual oil is displaced, when we see relative permeability curve, this is water relative permeability curve, and this is oil relative permeability curve. When we, so this is SWR and this is SOR. And when we inject surfactant and SOR is decreasing, then water relative permeability is increasing and water can flow much easier. Then this has some problem. This increasing water relative permeability gives mobility ratio unfavorable. Water can flow much easier, so water can bypass it, and it will give mobility, viscous fingering and mobility ratio unfavorable. So how we can improve this problem? If we mix only surfactant, then surfactant have surface adsorption problem and this mobility unfavorable problem. So we designed more complex process named micellar polymer flooding, which we mix surfactant with polymer, and polymer gives high viscosity. So polymer pushes surfactant and it reduces viscous fingering. And also micellar is this material. When surfactant concentration increase, surfactant itself, it locates individually, but at certain concentration, it makes city like this. We call it micelle. So even though total surfactant concentration increase, monomer concentration does not increase as well. So we use micellar, and micelle support fluent surfactant to the injecting fluid, and also polymer and micelle gives better mobility control. And surfactant property, surfactant is just like it look like sperm or just like tadpole. Head is hydrophilic and tail is hydrophobic. And this is just like oil. And this head sometimes ionic, and this is oil is non-ionic. So these two material locate. Okay, this head is hydrophilic and tail is hydrophobic. So it's located in the interface of oil and water, and they decrease interfacial tensions. And the laboratory and the field test result, and micellar polymer systems laboratory test gives recoveries over 90%, but in the field, actually, it's about 30% or less. Why? It's because of reservoir heterogeneous. Reservoir is not just like ideal formation. It's very heterogeneous. So still, surfactant and micellar polymer flooding has advantages and disadvantages. They have their own areas. It's good for using surfactant flooding and MP flooding. Now I try to explain about polymer flooding. And about polymer flooding, if we see making money on if we see the economic side of oil industry, then oil recovery and oil price is revenue. And when we do polymer flooding, polymer cost and cost of wells and equipment is cost. So we have to think these two sides. And what is polymer flooding? Polymer flooding is we mix polymer to the water. Then people, they ask about some strange things. Polymer is just like water. Basically, mainly polymer is from oil, and the polymer is not soluble, usually not soluble to water. But there's a special polymer who is water-soluble polymer. And most of polymer is not soluble to water, but some special kind of polymer is well dissolved to water, and we pick up that polymer and mix with water and inject to the oil field. And usually there's polyacrylamide is well used polymer type. And this is a single five spot pattern. And this is injection well, and this is production well. And when we start polymer flooding, we do pre-flush to condition the reservoir. We have to fix suitable salinity, suitable pH, and we have to do pre-flush. And when we inject polymer, then oil bank is made. And this is polymer. and this is freshwater buffer, and this is driving water. So when we do pre-flush and we inject polymer and we inject buffer water and driving water, then it just look like piston-like displacement, and it gives favorable mobility control. So polymer is mainly control mobilities. So polymer viscosity is high and mobility ratio is low. That's favorable mobility ratio. So it increase macroscopic sweep, also microscopic sweep efficiency. Polymer has two functions. First, it's so viscous, it's so it's much better than water to make piston-like displacement. And sometimes when we have channel, we plug polymer gel, and we remove those channeling area by using polymer gel. So mechanisms of polymer flooding. After water flooding, we can see so much residual oil. However, after PAM flooding, we can see much less SOR. The current polymer flooding project in the world. Okay, this is 3 representative chemical flooding. There's polymer flooding, alkaline polymer flooding, and ASP, alkaline surfactant polymer flooding. And mainly, China, they apply and they are successful in chemical flooding. Other countries, many other countries, they are focusing on thermal flooding and miscible flooding. But China, they focus on chemical flooding a lot. Okay, worldwide EOR production, thermal flooding is major. And next is gas. Chemical is very small. And if we see United States, still thermal, gas, and chemical is very small. However, China, EOR production by major process, lots of polymer flooding and steam flooding. Gas flooding is very rare. Okay, and personally, I like alkaline flooding because it's so cheap. Because when we see the price of chemical, alkaline is just like trash. I mean, very, very cheap compared with polymer. Surfactant is the most expensive. Next is polymer, and alkaline is the cheapest. And when we make soap, we mix oil and some alkali, and next day we can have soap. And naturally, acid fat is existing in the oil, and we inject alkali, cheap alkali, then surfactant is made in the reservoir, and reservoir productivity will be increased. So alkaline water flooding, I explained it. This is from water, this is from oil, and we inject alkaline, then we can have surfactant. Okay, then what is important in alkaline flooding? Oil should have high acid number. High acid number is milligram KOH per gram. So not all the oil has high KOH number. Usually heavy oil, heavier oil has higher acid number. Usually an acid number greater than about 0.5 is needed. So when we inject alkaline is very cheap, and alkaline has in situ surfactant manufacturing. We can have surfactant generating the oil field, oil reservoir, then we can have better production.
Professor,
However,
you still have 5 minutes left to complete,
okay.
and then we have Q&A session. Thank you.
Okay. Okay, so alkaline flooding have some problem, but it will be very useful. And I have several presentations, but due to time limit, I think I will stop quickly. And screening criteria, very useful screening criteria. And next is my lab. And you can see familiar face. I have several Indonesian students and Vietnamese students. And these are from Indonesia, and Libyan student and Kazakh student. And many years ago, we had big size of lab, not anymore. Yeah. Okay, I had several government-funded EOR projects, and Professor Asep helped me a lot, and we had again good cooperation and published a lot of paper and good achievement. And I think I will send my EOR presentation to ITB, and you can use it and you can ask me later. Okay, I'll start my presentation here. Okay.
All right. Thank you so much, Professor Bay, for your engaging lectures on EOR partnership implementation. We also have a very great fundamental lectures on EOR here. And now we already have a question from the audience. So thank you, Professor Bay, for your great presentation from Ms. Periska Rasma. And during your project, how much the EOR can recover the oil in reservoir? I think it relates to how is the actual recovery factor that you have achieved in your EOR projects. And also by injecting the polymer and CO2 to the reservoir, could we squeeze more oil to the ground while help fighting the climate change? Thank you.
Wow, wow, that's really fundamental, and take some time to answer all of aspects. Okay, about recovery, and second, climate change. Many interesting topics. About recovery, that's controversial, and about recovery of primary recovery, it depends on driving mechanism. Usually 10 to 25, 30% from primary recovery. In Indonesia, I visited several oil fields, and they stopped after primary recovery, and they start drilling, just drilling. But instead of drilling, I hope they do water flooding, and they do secondary recovery, and do EOR project. Then they can have better result. And usually after water flooding, depends on driving mechanism. Like water drive itself gives 50%. So water flooding does not give more. But gas cap drive and solution gas drive, you can have several sizable recovery addition. And recently, CO2 injection and the CO2 storage is big target. And as long as you have CO2 source, you can inject CO2 to oil field and get additional oil recovery, and you produce oil and CO2 again, and by the boiling point, CO2 can easily differentiate from oil, and you capture it again, and you permanently inject to oil field. This is really good plan, and many engineers think about this. This is a very good topic for further future research. Okay. Hope more time I can answer more.
All right. Yeah, maybe for I think a lot of audiences here still have a lot of question for Professor Bay. So maybe later on you can contact Professor Bay. I think is it possible that we
Yes.
share your email, Professor?
Yes.
Yeah, yes. And also for the lectures here or for the keynote speech here can also be reviewed in our YouTube channel in FTTM TV. So we will not share the presentation, but yeah, for the audiences can view the session later in the YouTube. And thank you so much, Professor Bay, for your engaging speech.
Okay.
And I think that concludes our second keynote session speech for today. And thank you everyone for attending this conference and for your discussions. And now I think I will let Mr. David Sahara to lead the concluding session of our conferences. Thank you so much. And I'm sorry if there are some words that's not convenient to you. Thank you.
Thank you, Mr. Bilal Aslam, for convening the second session of our conference. And on behalf of the committee, we would like also to thanks again to Professor Jian Zhou, Professor Ki Bok Min, and also Professor Bay for a very interesting talk. And now we have come to the end of this conference, and we would like to ask our Dean, Professor Rido Kresnawatimena, to give a concluding remark or close the conference.
Okay, thank you, David. So once again, on behalf of Faculty of Mining and Petroleum Engineering of ITB, I would like to express our thanks to all the speakers. I know probably, I don't know if you have your breakfast yet, Nick. But thank you very much. I think it's dinner time in Seoul and supper time in Melbourne for Professor Zhao. So again, thank you very much. I hope we can have another occasion for sharing knowledge, sharing experiences, sometimes in the future with more confidence way. Let's hope that this COVID-19 pandemics will be go, so we can meet directly sometimes in the future. So once again, thank you very much, professors, for giving your presentation. So thank you very much, and back to you, David.
Thank you, Parido, for the closing. Before we really end the conference, I would like to invite all of the panelists to open the camera, and we will have a photo session for the panelists. Pak Adi, could you please help us to take the picture of all the panelists?
Professor Sri. Professor Sri. Pak Ili. Koike Sensei.
Okay.
Adi, please lead the countdown.
Pak Ili, kameranya belum, Pak Ili.
Pak Ili.
Yeah.
Sorry.
Oh, he's already in the gym.
Yeah. Sorry.
Thumbs up. Thank you.
Thank you.
Thank you.
Thank you all.
Everyone.
Thank you all.
Thank you.
Good evening in Korea.
Yeah.
Thank you very much.
Yeah.
Thank you, Professor Min. Thank you, Professor Bay.
Yeah.
See you again soon.
Thank you, Professor.
Yeah.
Professor.
Bye bye.
Bye.